Welcome everybody to attend here today for the fourth day of the School of Electrochemistry. It's a great pleasure today to introduce our first speaker. I, I could supervise Dr. Gabriel in the beginning when he was undergrad student. It's a great pleasure for me. He's a special researcher, an amazing researcher. And I would like first to introduce him. And Dr. Gabriel, or Dr. Gabriel, obtained his PhD in chemistry in the University of São Paulo with an emphasis in electrochemistry and electrochemical techniques. After that, he started a postdoctorate in Warwick, UK from 2018 to 2021 in Patrick's Ewing Lab with a Marie Curie Research Fellow. Have a large experience in the fabrication and application of nanometer size electrodes for both high-resolution electrochemical images and probing biological interesting systems, such as living single-cell and single bacterium. Experience on the development of new electrochemical tools and techniques having helped on the development of new scanning electrochemical probe microscopy techniques, on the development of cheap and accessible scientific instrumentation aiming at promoting scientific development on underdeveloped regions. Gabriel have a large experience to create potential stats and with a great work with amazing number of citations to fabricate potential stats. It's a great pleasure, Gabriel, to have you here to talk with this audience, and the stage is yours now. Thank you very much.
Thank you, Tiago. Thank you for the very kind introduction. Before I start, let me just check if I can properly share my screen.
Perfect.
Let's see. Can you see my slides?
Perfect. Is everything okay? The slides okay?
Okay, perfect. Let me just go
Is
back.
everything good? It's with you now. Thank you.
Thank you very much, Tiago. Okay, everybody. First of all, I have to thank Tiago for this very, very kind introduction, and also to thank Tiago for this opportunity to be talking here. As Tiago mentioned, I did my PhD, University of São Paulo. I did part in Warwick, but mostly in São Paulo. And Tiago was effectively my supervisor when I was an undergrad, and then I went to be supervised as my PhD position by Mauro, which you guys were taught yesterday. So I do feel I'm home here, and especially this School of Electrochemistry I'm very fond of it. It's very close to my heart because I have been taking part as a demonstrator in this school since 2008, essentially on and off, of course, because of I was in Brazil. But I quite like this. I quite like the format. I've been afforded this opportunity to be teaching or to be participating since 2008 from Roberto Torresi, from Susanna, from Mauro, from Tiago. They are organizing, and I'm quite keen on this. So I really hope you guys are enjoying this whole week. I know it's quite a lot. It can be overwhelming, but I think it's a great opportunity. It is for free, and I know for a fact that it changed some people's career path towards electrochemistry, and for sure it helped change mine and to put me where I am right now, or at least my career path. So enjoy the most. I know this virtual format is not the easiest one, and I wish we could be face to face here. But we can try to engage. You can try to talk in the chat. I know that Mauro was quite engaging, and I will try to bring the best Mauro in me and see if we can talk a little bit. So feel free, ask questions. We'll have technically an hour and a half. I learned that with Roberto, that there's not good history you cannot tell in an hour or less. So if you guys engage, you can use that full 1 hour and a half, and maybe it's going to be a better value for you. So science-wise, today we're going to talk about reaction mechanisms, and more specific about the coupling of heterogeneous and homogeneous reactions. I'd like to do a disclaimer and to give credit, of course. I think in academia that's quite important. These slides, they are very based on Guy's slides and Tiago's slides, which they gave this lecture several times. Of course, I put my own twist on it, but it's important to recognize in academia we always build upon other people's work, right? On the screen here, you can see my details. I think it's going to be more important tomorrow. We're going to have another talk tomorrow where I will talk about what I did my postdoc specifically. But if you have any questions, I think just give it a shout. So, okay, let me just see if it's working. And okay, so before we start, I'd like to kind of recap a little bit what you guys have seen so far. And you had plenty of classes, and essentially those classes, they come to electrode processes, which you saw absorption and electron transfer. Hopefully, just a disclaimer, I wasn't able to see all the classes, so I'm kind of basing on the things that I know from past years. From charge transfer phenomena, you saw electrodic kinetics as well, right? And these you saw a lot of Susanna. Guy as well, most likely talk a lot. You saw mass transport, which is quite important as well. And you saw some techniques, mainly CV with Mauro yesterday. And here I would just like to do my first parallel for my first tangent, and I probably will do a lot of those throughout this talk. That the importance of CV. Electrochemistry has many techniques, and especially in this talk, I will focus on CV again, not only because hopefully CV is quite fresh on mine because of Mauro's talk, but also cyclic voltammetry is an amazing technique, and it's quite informative, and it's a nice, it provides a nice way to investigate into C systems. So we're going to come back to the CV later, but just if I show you this classic CV here in the corner, which you guys now are quite familiar with, Mauro showed you this infamous duck-shaped CV. I always like to people to look at CVs in a different way. You have two axes here that have represent to you two distinct domains. And I'm going to say in quotes this because it's not completely true. If you remember from Susanna's talk and from Guy's talk, you know that this potential here is tied with kinetics somehow as well. But I like to see this as mostly a thermodynamic domain, or the amount of energy that I'm given to a reaction to happen. And the other axis, current, is just the speed of reaction, right? It's just the rate of reaction. So I have a very much kinetic domain here. So I quite like how CVs put those things together and allows us to investigate a system and to see how I can provide energy and see how the reaction happen, or what's the rate of reaction. Another amazing thing from CVs that we're going to look on throughout this talk is the fact that we can change the time domain as well, because I can change the swipe rate of my potential, right? So I have this ability to modulate as well, and this is going to be very important for us today. But again, it's just me trying to sell CV to you guys. It's quite an amazing technique, and that's why we focus on this school a lot on CV, even if we have many other techniques. So going back to what you guys have seen so far, so you have a lot of that. So if I present to you this CV here, and I'm presenting a system which I start with an oxidized species going toward reduction, right? And this is something throughout this whole talk as well. I'm always going to base on this. Like all the data I'm showing here is simulated. We can talk a little bit about that, but all assumes that we start in a solution that only has the oxidized species that reduced to red. So if I show you guys the CV, now you can explain pretty much everything from the system. I'm on my forward sweep here. I'm going towards reduction. You know why there's a known set of current at a given potential. You can explain why it peaks. You can explain why it decreases. You can explain why I flip the potential back. I still have negative currents, meaning that I still have a rate of reaction towards reduction, and why increases again, and blah, blah, blah. All these kind of things, now you guys are experts on that, and you can explain. One important aspect of that everything you did, and if I translate this to this rough cartoon, everything you guys seen so far relates to this interface here, right? If this is my electrode and this is the solution that I have, everything you investigated so far or you saw so far relates to this interface, the interface between the electrode and solution, right? So it's the interface between two distinct phases. That's why we call this a heterogeneous interface or a heterogeneous reaction. So that's why we say that an electron transfer reaction is a heterogeneous reaction, because it happens in this boundary between two distinct phases, right? And it's quite fair that we only look at that so far, because 99% of electrochemistry happens here, or is the things that we are concerned with. There's a disclaimer that this interface, although we like it and we study, is also the pain of our existence as electrochemists. And we're going to talk about that tomorrow on how we try to probe it and characterize it. But a lot comes from this interface, since that's where the reaction happened. So just on this cartoon then, from this heterogeneous reaction, and we're just changing the ox for this cartoon's sake to a metal ion, for instance, ferrocyanide or something like that. This encompasses everything you guys saw so far. So mass transport, though it doesn't happen at the interface, it provides material to that interface, so it's quite important. And once the material arrives to that interface, as long as my electrode is polarized in appropriate potential, as Mauro showed in his slide yesterday with the energy levels of the electrons, a few things can happen. You can have an absorption, which is also an electron process, but we're going to just disregard that. But to have a charge transfer reaction as well happening, and then this material is reduced here, for instance, I have the flow of current, I have a change of electrons, a flow of current, and then this material can either be transported back to the bulk of solution by the same transport mechanism you saw, or it can be re-oxidized in the surface if I flip my potential, right? So that's just to see everything you guys have seen so far. It's a heterogeneous reaction or relates to the heterogeneous reaction. What I like to pose to you guys now, it's a problem or a question to you. So what if either or both of my ox or red species are not chemically stable? And by not chemically stable, I'm going to go on my second tangent already now. I think most of us, we are chemists, we can think of not being chemically stable in a few ways. The basic way and the straightforward thing that just decomposes with time is not it has like a half-life or a decay per se, right? So that's what I'm saying here is red going to like a product, but it could be either red or ox. But you have to think that chemically as well, it could be a reaction with something in solution, right? As long as this other thing in solution, this other reactant is in large excess, it doesn't matter from. So imagine if it's water, if it's 55 molar concentration, if it's like a hydrolysis process that either ox or red are happening, the water doesn't take place in a way because the concentration is not going to change, right? So for all intents and purpose, especially kinetic wise, we can disregard. So that's just this tangent. I'm going to talk about this decomposition, but you think that this decomposition can be many things, can also be a reaction with something else. So what if both or either of them react? And maybe Mauro gave you a spoiler yesterday. I'm not sure if he got to that slide, but I hope you guys know the answer of that. But first of all, just say that this is kind of a silly question, like, because we could look at ox, we could look at red, but if you look at ox, and I'm posing to you that this system and all systems we're talking about today, they relate to the oxidation, that oxidized species being reduced. If I only start with ox and ox is not stable over time, the overall effect that oxygen is going to decompose. And when I start my experiment, I have a lower concentration, which does have implications. And we can talk about that if you guys want to, but it is definitely not the main focus. I think it's much more interesting. You think that red is not stable, right? So I'm just posing this question. And if you guys want to, you guys can answer yes or no in the chat if you have the energy in you. But do you think if red's not stable, would that impact my CV profile? And I'm just going to like 10 seconds. If no one replies, it's fine. I just want to see if you guys are just like paying attention, thinking about that. And if Mauro gave you or not a spoiler. Would that change? If red's not stable, would I see that on my CV? Right. And I guess, of course, the answer is yes. I would be able to see. Yeah, I saw some yeses coming here. That's nice. So for sure, I'm going to have it. And you guys are right. And I'm not sure if Mauro gave you the spoiler, but we're going to see. And I say like, yeah, I want to go back to reverse direction. So that's very nice. You guys are in the same ballpark. That's going to be an easy. We're going to fly through these lectures. It's going to be really amazing. So as we will, and I'm going to demonstrate to you guys that we can actually use electrochemical techniques, especially we can use voltammetry to study systems that look like that. So the question that I posed and you guys already answered, we can also, of course, we're chemists, we can talk about chemical reactions. So we have here a first electrochemical step that I'm posing here, which is the oxidized species reduces to red, which is followed by a chemical step, which the reduced species decompose to P, a product. P stands for product, right? This is an equilibrium reaction, as most or any reaction, which has a forward rate constant. It has a backward rate constant as well, right? And it also has an equilibrium constant here, which is the ratio of those two. For ease of understanding, let's always assume that Kb, the backward constant, is negligible compared to Kf. So we assume that's just probably a reversible process or near to reversible, right? So always we only concerned with the decomposition of P. We can look at that and we can write a rate law if you want to. And the rate law for red would be this minus K4 times the concentration of red. And that's just mean that this reaction here is just reducing the concentration of red over time. This process here, where does it happen in solution? So I talk about that we look at the interface of the electrode. Although this reaction might happen at that interface, tend to say that it happened actually at the solution. So not necessarily in the diffusion layer, throughout the whole spectrum, but the diffusion layer is where we're going to find those species, especially red species, when I'm doing the reduction. So I like to think that it happened in the diffusion layer, and I like to think that we're looking a little bit further into solution that heterogeneous interface. So that's a homogeneous reaction, right? Because it only happens in solution, either the decomposition or the reaction of something, right? So that's why we call this a heterogeneous, homogeneous reaction coupling. And as I mentioned, we have electrochemical step followed by a chemical step. Electrochemists were not very creative, so give a name for this reaction mechanism. We call the EC mechanism. E standing for electrochemical, C standing for chemical. Usually we have an index here, which is just the order of the chemical step. And since you already wrote the rate law for this, we know it's a first order. So this is just the EC1 process. And bear in mind, we can have EC1, EC2, EC3, and so forth, right? Well, you guys already replied to me, we're on the same page, that this would impact my CV. So how would that impact my CV? I like to tackle this problem in a few ways. First thing I like to do is to separate my CV into in two parts. And it might not be straightforward at first, but stay with me and I think it makes sense. So if I'm starting this system, and I'm also, by the way, just separating the reactions as well, I think it makes it a little bit easier. So if I'm starting only with oxygen solution, only the oxidized species that go and store that reduction, right? I can just suppose, well, first this reaction, we know it's an equilibrium, there's reverse. Let's think about that. So I'm starting DCV. You guys saw for everyone. If I want to reduce, I need to go cathodically. I need to go towards, well, smaller potentials. The case depends on day zero. Those data are all simulated, by the way. You guys are seeing simulations with the GUI. So I can choose day zero. I choose day zero for this process to be 0 volts, just for ease of interpretation. And I use a package called Comes Home with Physics, just because it's the package that I'm familiar with. And I'm aware that Guy is going to talk a little bit about the package. It's definitely an overkill for this. It was easy for me to use. And I'm using bottom-warmer kinetics on here, right, which you guys saw yesterday. So I think it's quite important. You saw with Suzanne as well, and a little bit with Vitor. Anyway, I think that was my third tangent of the day. So if you have this reaction, then let's go back. I'm starting a system that only have the oxidized species, and I'm sweeping my potential cathodically towards negative potentials here, towards reduction. If you want to be fancy, is my cathodically potential excursion, if you want to talk about fancy terms. So what I have is this, it's just half of a CV, right? I'm just going from no current until I have the onset of current, peak and decrease, right? Let's analyze this. We know that current is proportional to the flux of species, and I'm pretty sure Guy showed you guys yesterday the boundary conditions for bottom-warmer kinetics, how to calculate current, and that's it. It's just the flux of species that are being consumed or produced at that electrode interface, right? That's why current is the speed of the reaction. So we know current is proportional to the flux of species. The flux of species is proportional to a rate constant here, and that comes from bottom-warmer in this case, by the way, right? That's the rate law that I'm using here. That's the kinetics times the concentration of ox species. If you assume that ox species in this process, oxygen red, it's electrochemically reversible, it's diffusion limited, we can calculate the concentration of ox just by giving these equations, just Fick's law, and that's all fine and dandy, that's all well behaved. So in this peak, there's nothing going on. Someone in the chat already said, okay, you're going to see something in the reverse process, and it's absolutely right. Let's now analyze the other half, right? Let's complete our CV and let's go to our anodic potential excursion side. So here what happens is, first of all, I have the reverse process, of course, so I produce red species here. So if I flip the potential enough to oxidize them, I'm going to reoxidize the species, which is all fine. But I also have this chemical step coupled to it, right? I also have this reaction here, which is consuming red and forming products, which are not electroactive. Again, current's proportional to the flux of species. Same thing, I have a rate constant here. I have the concentration of red. If this was just reversible, just diffusion limited, I have my equation, and partially there's a diffusional aspect in component it's here, but I have to add this tiny term here, which is just meaning there had something removing red from solution, right? So there's this Kf in action here, this constant that's just reducing the amount of red, which means that my overall concentration of red is going to be smaller, meaning that my current is going to be smaller. I know it's hard to see that with those CVs separated apart, so we can put them together here, and I'm just showing some simulated CVs for different values of Kf. And there's some nice striking features here, but I think the most marked one is the decrease of the reverse process, as someone said in the chat already, right? So we can see that when I go from smaller-ish values of K to larger values of K, I have a significant decrease of this reverse current to a point that that current actually doesn't exist anymore. And hopefully it's straightforward to realize that this is just because the action of this Kf, that's just hijacking red from my solution, making the concentration being smaller, hence the current's going to be smaller, right? So my electrode doesn't see, and I'm going to anthropomorphize my electrode, it doesn't see enough red anymore, or the same amount of red it would, to a point that actually doesn't see any red, just because I'm consuming this. First things before we, one thing before we keep going here, I just like to stress that out. Look at the units of Kf, like it's 1/2. So there's a hint there. There's a temporal aspect that is going to be important in the next few slides. So hopefully that's fine and it makes sense to you guys. And oh, someone asked like the green part's because it's too slow. The green part is because this here, the green CV, we're going to talk about temporal aspects. The green CV is because this constant so high, right? This constant so high that every red that's produced here, it's very fastly consumed. So in the time frame of this experiment, depending on this, the cyclic voltammeter rate, and I'm jumping a few slides, all the reds consumed by the chemical step, right? So there's no red in front of my electrode, it doesn't see anymore. But this hopefully will become clear if we have a look at the concentration profiles in the surface of my electrode. I think it's a useful thing to see. Experimentally, it's hard to see. There's an argument that the currents of the CV, they are already the concentrations because they're proportional, right? And yeah, oh, sorry, I'm just following the chat. Yeah, it's dependent on the scan rate. We're going to see that in I think 2 or 3 slides. But I think it's going to be easy for us to understand if we look at the surface concentration of the electrode. And again, as I said, there's an argument currents are surface concentration in a sense, but the part of the simulation is that I can actually go there and probe, right? So I'm just showing here just a cartoon. Well, this actually is the simulation experiment, but just so you guys can understand how this simulation happens. So this is just a cross-section view. So I have my electrode here is the black part. This gray part is just insulators. Every electrode is we have a fine area, and it's just a simulation of a diffusion layer, essentially concentration, right? As I said, I did that using COMSOL. Guy's going to talk about straightforward simulation, quite simple. We could talk about that if you guys want to, but I think also Guy's going to cover anyway. But the important thing for me to stress now is that I'm looking at the concentration at this very finite boundary between the electrode and the solution. And just to be, I know it's a terrible PowerPoint kind of Photoshop, I'm just kind of flipping that cartoon that I showed you guys, just so we're understanding that the simulation is essentially representing that, right? And just have an electrode, I'm representing mass transport and I'm representing electrode kinetics, right? So it's very straightforward. But I run the simulations and let's look at the concentrations at the surface. So I do think they're going to be quite helpful for us to understand. If we look, I'm presenting 3 concentration profiles here, and I'm just going to put in the corner here the CVs. I think it is easy. We can assume that this is a small one here, this is small KF. It's almost reversible, it's not quite there, but let's assume it's 0, right? So that would be this case. If my KF is 0, if I don't have a chemical step, what does that mean? It simply means, right, that I just have a reversible electrochemical system. And that's what I'm showing you guys here. And I don't want to waste much time, but it's just, I don't know if Guy showed you that, and Mauro, I think, did. That's just a very characteristic concentration distribution profile. This simulation is starting with 10 millimolar, that's why it's 10 millimolar, so you don't get hanged to that. It is over time, but remember, it's a cyclic voltammogram, so when I sweep in the potential, there's a scan rate dependence. I put the potentials here at the top. But this is a very important aspect. We're seeing concentrations over time, right? So bear that in mind. I start with oxidized species, and nothing happened with time because I'm in the potential that is not enough to reduce into a point that I reach that enough potential, I have the onset of current, I start consuming ox at the same time I start to produce red, all fine and dandy. So the concentrations, they kind of flip to a point that I reach here that my surface concentration of ox is 0. And that's a very important point that I like to, maybe is my 4th parallel here. That's when we got a diffusion limited state, right? That's a characteristic of diffusion limited process when our mass transport limited, where the concentration of the surface is 0, right? That's when it happens. At that point, the red concentration is the maximum it will ever be because it's a 1-to-1 conversion. And more importantly, within the tangent is that people should realize, and people sometimes think, oh, that's the peak current. And that's definitely not the peak current, right? When you're in the peak current of a CV, you still have a fair amount concentration of ox in solution. Well, I have no ox to be reduced, so it doesn't matter how negative my potential is until I flip my potential and I get anodic enough that I start now to consume red and reoxidize ox, and that's why they just mirror each other, right? So it's quite fairly simple and straightforward. Okay, so that was the simple case, right? Now imagine that I do have a couple chemical reaction, and that's that case that I'm showing you guys here. So a few things are striking already, right? It's the fact that the concentration of red never reached the 10 millimolar. And not only that, it decreases over time, right? The concentration of ox is 0 at this point, so there's no conversion more, but you can see that the concentration just decreases with time. right? And that's an important aspect. Although my potential is still very cathodic and can reduce, the concentration is just decreasing. And why is that? It's just because we're just looking the action of this KF, right? We're just allowing this reaction to take place because we're just sitting there kind of waiting. And of course, this is in quotes again. So the concentration decreases. And by the time I flip the potential to where I can reoxidize red, you see that the concentration of the surface is much smaller now. It's 3/4 of what I start with. So the current is going to be 3/4 of what it is, because that's what my electrode's seeing. And that's roughly what you see with the red curve, right? Is a 3/4 kind of conversion. I think it's easier to see on a very fast kinetics, which would be the case for the blue line here, where I just have like a short peak of red because most of it's being consumed by the chemical step. And then you can see this large decay over time. And this large decay is just because, again, because of my scan rate, I'm staying a lot on that region, and I'm affording time for this reaction to happen, right? So hopefully this is clear and you can understand the temporal aspect of it. So I'm hammering a lot on this temporal aspect. You got chat as well, or on point on that. So of course, there's an interplay between the KF value and my voltammetric scan rate, right? It is a time-independent aspect. So those are simulated data as well. This axis might look a little bit confusing, or the units is not quite there for guys, not currents. And that's going to be just like a 15-second thing if someone wants to put a chat. Do you have any idea why I'm normalizing by the square root of scan rate? Just a 15-second while I take a sip here. I know there's a delay, but okay, no one. Okay, that might be a hard one. It's fine. Remember, if this is a diffusion limited process, the electrochemical step is a diffusion limited process. The peak current should scale with the square root of the scan rate. So because those are CVs that I'm recording at different scan rates, they all have different values and different magnitudes. So by dividing by the square root of the scan rate, I'm kind of scaling them down to the same value, and everything should be fine. It doesn't work perfectly because of reasons of kinetics here in this case, because of the couple step, but at least they are now on the same part, and it's not very stretchy and hard to visualize, right? So this is just an attempt to normalize things. And always remember, if it's a diffusion limited process, the peak current is proportional to the square root of the scan rate, like it's Rundle-Sevig in a nutshell. But anyway, maybe the sixth tangent of the day now. Let's move on. Let's keep going with this time-dependent aspect. So those CVs are just recorded at different scan rates, right? And although I'm not showing different scan rates, it's because electrochemists, we like our constants, and there's this mentioned constant K, a capital K, that just kind of shows us like a relationship between KF and V. So the larger is my scan rate, the smaller the value is K. So the smallest one is blue, and the opposite is right. The lowest scan rate, the larger the value is K. So that's going to be 1, right? So you can see as fast scan rate, intermediate scan rate, very slow scan rate. So what explains that? And there's a few ways you can think about it. And I think thinking about half-life or stability, it's quite useful in a sense. We can think about that red has a half-life or instability, and that's just the action of this KF going on, right? So the faster the KF, the more red they decompose. Or for a fixed KF, which is the case of those simulations, the slowest my CV process, the more time I afford to that constant there to remove K from my solution, decreasing this process. We can we can resort to surface concentrations once more, if that makes easy for you guys. So I'm just pulling back one of those concentration profiles, and I'm seeing sort of for the intermediate here. They don't match quite properly, but it's illustrative. So remember, if this is a time axis, and well, I'm flipping the potential between here and here, right? And this is a time axis. If I do a very slow scan rate, let's say that I took this time to reach from the peak potential to where I start reverse oxidizing, I'm allowing that amount of time here, I don't know, like 6 seconds or so, for that amount of red to be consumed by action of this KF. So how can I avoid that, or how can I change that? Well, I can simply scan faster, and instead of flipping in 6 seconds, I could flip the potential much quicker. So this is just, of course, illustrative here. I didn't change the concentration profile, but I imagine that here I'm flipping the potential back to oxidation. You can see that now the amount of red that I lost is much smaller, right? So that's the interplay between KF and the temporal aspect. And I think it's quite important to understand that and to think, because remember that I mentioned on my second slide that CVs are amazing because of the fact that now I can also, besides the thermodynamic kinetics kind of thing, but the fact that I can change the time domain and I can modulate it. So this allows us to modulate the time domain and see different behaviors in CV. And why is that important? Is that let's assume that me, Gabriel, I have a system that I imagine is maybe an EC1 process. How do I go investigating that? I just record a CV and I see some features that are like telltale signs that might be an EC1, but I need more information, right? Would be very nice to see this interplay, to be able to see this change, for instance, in peak current, the reverse peak current, with different, either with different KFs values, as I showed you guys previously here, like in the corner here, or with different scan rates. So the fact that KFs I cannot change, like they're inherent from the process. Actually, not true. I can change. You can make an argument for that if I change temperature, for instance, but that's getting quite fiddly, right? So if I'm recording experiments at same temperature, I can use another resource. I can use the powerfulness of CVs to just change the time domain. And then I can see the interplay between how I change my scan rate and how this current increases or decreases. And that gives me more information about the process. Another thing to bear in mind of this interplay as well is that although it helps us understand, it also means that if you record a simple CV from a system and you don't see, for instance, if I record a very fast CV, I record at 500 millivolts per second for any given reason, and I see a very reversible system, peaks here, but I'm not sure, like that's kind of an unknown system. I'm not talking about Huhex, I'm not talking about ferrocyanide, I'm talking about something that we don't know. Some synthetic chemistry give you a compound and you run one CV and that's it, golden. So yeah, it's mass transport limited, look at that, Handelsevik, all good. Well, it's not true, is it? Because maybe we're just out of the range of the temporal resolution of that scan rate that we're not able to see. Remember, there's this interplay here. So you need to record at slower and slower scan rates just to make sure that you are not seeing this, make sure that you can capture that kinetics. There is a caveat on that as well, and I'm not sure if Mauro mentioned, I think he did. If you scan very, very slow, you start to get away from your diffusion limited process, if it is diffusion limited, because you start to have natural action taking place, and that might change your current, and that might skew that relationship, right? So that's just for guys to bear in mind those things, those aspects. So there is this interplay, and we can use in a nice way for us to study, but also they can limit a little bit our analysis, so you need to be very critical about it. There's another striking feature on that CV that I don't know if any one of you guys got it. So the CV of the different KFs, not the different scan rates. So I'm just bringing them back here. So these simulations for same forward rate constant for that chemical step. So I said that there's this striking decrease here, but also if you look at here, besides the current changing, there's a clear shift in this potential, right? And because we simulated, I think it's quite easier to see instead of looking at this shift. Let's look at the concentration profile for all those simulations of ox. Now I'm just zooming in a section, right? Where you see here, remember, time is potential as well as the CV. So I'm sweeping my potential here, and at some point I have that onset, right? That which I start to consume ox. And if I do that for a bunch of KFs, you can see that there's definitely a trend that the larger my KF, the sooner I start to reduce that species, right? And the sooner in time means sooner in potential. I was gonna ask if you guys know why it's that, but I just realized that I forgot to put an animation here, so answers right here. But it's something that's a lot, like it's overseen by a lot of electrochemistry. Sometimes people don't think about that. That is just an artifact of you shifting the equilibrium, right? If I do have this chemical reaction here, this is also an equilibrium reaction. So I have reactants giving products here. I have a couple step after that, the homogeneous couple step, which just consumes one of my products, right? So I'm essentially just shifting the equilibrium. I'm just literally Le Chatelier principle, shifting that equilibrium, meaning that I'm shifting this equilibrium. I'm making that reaction happening more and easier. Remember of the analysis that I talk about CVs that I like to see, and I'm putting quotes here because again, it's not 100% accurate, but thermodynamic domain, kinetics domain. If anything happens for reduction, we're assuming that this reaction has an E0 of 0. So anything negative, I'm giving energy for reduction. Anything positive, I'm giving energy for oxidation, right? So the more energy I have to give, the more negative, the harder this process is happening. The less energy, the easier this process is happening. So if I'm shifting towards shorter times, I'm shifting towards smaller cathodic potentials. I'm shifting towards zero, meaning that this reaction is happening easier and easier, right? And this is just because I'm shifting the equilibrium. So this is important to bear in mind that it does happen, and we see taking place in many electrochemical systems. And it's just because we have to understand this is an equilibrium reaction as well. We are removing products from it, or not removing, or even if we're putting on. So there is this trade. Telltale signs. So I'm just going to ask now, is everything okay? Any burning questions? Because after that, we might move to a different system a little bit. We can always ask questions, but if anyone has any burning question now, maybe it's a good time. Okay, so one saying that all okay, good. I appreciate you guys participating. I know it's a little bit complicated and fine. All good, thanks. Okay, cool. I would take 2 as representative, but I'll keep going then. Fair enough. So some telltale signs of an EC1 mechanism, and not only EC1, right? To an EC mechanism, just EC1 here because the one we're seeing. So first things, the ratio between my back sweep peak and my forward sweep peak should be smaller than 1. And that's just meaning that my back scan is going to be smaller, as we saw in LCVs, right? So the ratio of them is going to be the forward scan is much larger than the backward scan. And as we mention all the time, and hopefully I passed the message, this is depending on scan rate, right? It's depending on the KF, of course, but it's depending on scan rate. So there's a proportionality here. So you can change your scan rates and see the ratio of those peaks, and that gives you some information about this. So this is a telltale sign, you know, we're dealing with a EC mechanism, at least. Not necessarily an EC1, but an EC mechanism. So look at the ratios, scan different scan rates, and see if this ratio changes. And remember, the smallest the scan rate, the smallest is going to be your reverse peak. There's a slight decrease of this ratio here, the forward peak with the square root of the scan rate. When the scan rate increases, it's also telltale, but it's very small. So I wouldn't bother that much with this. It's just textbook kind of thing. Important thing that also is small and hard to quantify sometimes is the shift towards the reaction happening easier. So in our case, less negative potentials, but that's a nice telltale. We're shifting that equilibrium. And this one, I quite like this one because it's quite informative, because although we're seeing this shift, we can actually quantify. So there's a relationship between the delta E peak and the delta scan rate. So for every time you change by a 10-fold your scan rate, if it's an EC1 mechanism, that peak will shift by 30 over n millivolts. And if it's an EC2, you change by 10-fold, 19 over n millivolts, right? So that's quite a diagnostic tool that helps you understanding what's going on and which system you have. There are examples, yes, there are definitely examples of that. And I'm just using one from Compton's book, which I don't think is, well, it is relevant for a lot of people, but it's not the most up-to-date one. But I think it's nice, it represents that most of the systems you see or those stuff, they happen to more complex molecules. Sometimes electrochemists would like to make things easier. We like redox reversible couples, and you're rarely going to see that. But if you go like for organic molecules, you go for DDP, for instance, it can go a reduction, but it can also dimerize to something that's not electroactive, right? So if you already see from the first EV, that's not the most reversible system anyway. So that's why I don't like that much, this system, but anyway, it's very characteristic. But you can just see that if I increase the scan rate, that reverse peak starts to appear here again. And also don't mind that the potentials and currents are flipped, it's convention stuff. But you can see that I have a reverse peak appearing when I increase my scan rate. And if I decrease my scan rate, I don't see the reverse peak. I'm starting scanning from here. So that's quite characteristic. A lot of things like ascorbic acid can do that, although it's very fast kinetics. You need to have a very, very fast scan rate to be able to see the reverse process, but you can. Caveats on that, the faster the scan rate you have, remember you have other problems like capacitive current, which gets tricky and starts to blur signal. So, and we might come to that point in the end of this talk if we have time, is that although I like CVs a lot for visualizing and understanding, I think they're quite informative, they might not necessarily be the best tool for that analysis. And we're going to mention that tomorrow a little bit as well, more related to electrokinetics than couple reaction kinetics. But it's horses for courses, right? You have to choose the proper tool to analyze the system. And sometimes CVs might be a little bit hindering on that case, that if you fast, you have very capacitive current. And CVs on big electrodes, of course. I don't think Mauro got to that, but you can decrease the size of the electrode. You can have hydrodynamic voltammetry. You can have plenty of other techniques that mitigate somehow this. They have pros and cons, but just bear in mind that I think, and that's my personal opinion, that CVs are very good for information-wise, visualizing, and they are for sure a quantitative technique, but I prefer it as more like a diagnostic technique than anything else. Well, let's extend on the EC mechanisms then, right? This is a very particular EC mechanism that we call the EC prime. Prime is this tiny guy like right here. And what that implies too is that this is a catalytical process, a catalytical cycle. So why is that a expansion of EC? Because I still have my electrochemical process here. So I still have oxygen solution being reduced to red. And I still have a couple following step, which is the chemical following step, which I have my red in solution. This case, we can think again, that's probably tangent 2 that I'm just revisiting now. We could having it naturally decompose into something, but most of the times we put that as reacting something. I'm going to explain why. But the important thing is that on the chemical step, red reacts with something and produce something that's not only electroactive, but actually produces bad COX, right? That's the catalytical aspect of it. So a nice way to think that, or to see, in my opinion, is that you have here electrochemical reduction step, and you have a chemical oxidation step, right? So they complement each other. So the heterogeneous reduction is complemented by a homogeneous oxidation in solution. As any reaction, forward constant, backward constant, we assume that backward constant is negligible compared to F, just to make our life easier, right? Of course, there will be impact if it's not, it's an equilibrium, it gets way more complicated. And we're going to talk about that later, a little bit about complications of this subject. And not only EC prime, but a couple reactions on so. But anyway, coming back to the system. So if that happened, if I have R, and for, again, clarity's sake and for easiness of understanding, let's assume R is in excess. So that's why I mentioned that this could be like a natural decomposition to something. But the fact that it's being reoxidized again is weird to be a natural reoxidation. So usually it's reacting something, right? So if it's being reoxidized, R is being reduced to something. But let's assume R is in excess now, because that's going to make our life much easier. I can go the same route. We all agree here, and we all know that current is proportional to concentration. So we can the same route and try to write laws for the concentrations and how the concentration change of the species. We have the concentration for ox, which has its diffusion component here. Oh, sorry, let's start with red. Apologize. We have the diffusion component of red, just like we did, and we have that Kf constant that's just hijacking red from solution, right? It's just removing it from solution. But now if I write to ox, it's not the same as was before. It's not only the diffusion aspect of it. I have a term here that's actually adding ox to my solution there, right? It's adding ox to the surface of my electrode, for instance, right? Which with the same rate as the decomposition of red, because again, it's a one-to-one kind of thing, right? For every red that reacts with R, I produce one ox. So now you can understand already why I'm going to have an impact on both my reverse peak, as I had for EC1 mechanism, but now I'm going to also impact my forward peak current as well, because I'm increasing the concentration of ox. It's just that simple, right? So if I show you guys some simulations for this system, we can see when my Kf is a little bit smaller, and it does have a different unity here because it's not necessarily a first order reaction is reacting with something, just bear that in mind. If I have a very small Kf, you can see I have almost a reversible peak here. It's not quite reversible. The ratios are a little bit different because it's not zero, right? But it's quite small. But you can see when I increase the value, a few things happen that are quite striking, I think. So I'm increasing that direction, right? From black to this purplish thing here. You can see that I have, if you look at the reverse peak, a massive decrease, and that's expected. It's still a EC mechanism, right? Those are is a specific aspect mechanism, is the EC prime. So that's what expected. But now my forward sweep not only increases quite a lot, but also you can see that the CV changes shape, right? And starts to become less peaky and starts to become more plateau. I'm just check on, okay. Before we move on, I'm going to again afford you guys the opportunity to think about, you don't have to answer if you don't want to, but just think about what you guys think is going on here. Like, is this an indicative of something that you learned recently? I know that Mauro didn't go to that point in this talk, but is there a CV that's quite similar to that? that you guys are known of. So we saw macroelectrode CVs, we saw the peak shape. Is there any CV that gives this kind of sigmoidal shape? If anyone wants to say, no pressure, but like, do you know any kind of electrode that gives this kind of behavior? Yep, study states rich. CV is not controlled by mass transport, microelectrode. Yep. Not polarizable is not the case, but yeah, a lot of microelectrodes, a lot of mass transport. And that's the key. That's all that I want for you guys. Mass transport, right? We're going to talk about that right now. That explains for me at least quite a lot of the EC prime mechanism. And I'm going to bring you to this journey of mass transport in EC prime mechanism, right? So yeah, this is a very characteristic thing of changing in mass transport. In this case, not only mass transport, like it's not only controlled by mass transport, we have a kinetics aspect to it, but just to try to make parallels to it, that we're changing the mass transport aspect here, or the mass transport is not dominating anymore. Because if it was mass transport dominated, we would have a reversible system. None of those electrodes are only mass transport dominated because they have the couple reaction. But there's something very special here that makes this shape changing a little bit. So I'm going to pose again that we look to surface concentrations, and they're not going to be useful at all to us at this moment, right? Maybe an in-depth analysis of the time shift aspect would be nice, but they can't explain, right? That's not the route I would go to explain EC prime mechanism. I think it's more interesting if we look at a concentration not across the electrode, but from the electrode to the bulk solution, right? Let me just see, there's a comment here, this ox produced in the diffusion layer. Yeah, so let's see if that's real, let's see if that's true. So I'm proposing now that we look, and this again is a cartoon. Remember that the last time we look at it, we look at this interface right here, right? This very thin layer. Now let's look actually this line here. So let's look from the surface of electrode, which in this graph corresponds to 0, going towards the bulk. We're looking across the diffusion layer thickness, essentially. We're looking at a gradient of concentration, right? So if I look at that for 2, and here because simulation is easy, although not only simulation, and we're going to mention that EC prime has its benefits since you react with something that I can actually turn on and off the system, which is a very useful tool for analyzing. But if I'm looking at only electrochemical step and then the electrochemical catalytic cycle step here, I have these 2 different profiles of concentration. Again, 0 is surface of the electrode going towards bulk. And these were just simulating to like 800 micrometers or so from solution. Don't bother with the units and size. This is definitely related. Mauro told you guys yesterday that the diffusion layer thickness is a temporal dependent thing, but also the size of the electrode thing. Like there's a lot of aspects going to, but depending on the scale of electrode, it depends on the size of the electrode. But anyway, have this concentration profile, which I have for both cases. This is taken from the most cathodic potential that I can have. So the end of my CV, the most reductive, and in our case, minus 0.4 volt. Like, so this is the thicker the diffusion layer will ever get for that system. At the surface of my electrode, for both cases, I have 0 concentration for the Hawk species, which is great. But then I can just see that for the electrocatalytical cycle, it returns to bulk values to 10 millimolar very quick, right? In a very short span of length. Now for the electrochemical one, it takes way longer. It does come back, but it comes back at, I don't know, 500 or whatever here. This is, by the way, and I'm pretty sure Mauro showed that, this is one way we can calculate the diffusion layer thickness, right? So if you just put the intersection of those 2 lines here, so the linear part of the concentration here with the bulk of both of those intersects are just the diffusion layer thickness. So the diffusion layer thickness of those 2 systems is vastly different, right? And I think it helps us to look at those. So those are the simulations, right? So you can see that for the electrochemical, for the couple reaction, the EC prime, the diffusion layer is way thinner than for the E1, for the electrochemical aspect. And this is simulated, by the way, for the same electrode, of course, same scan rates. The only thing is one is on and off the prime aspect. So there's a few ways you can look at that and try to explain why I have an increase in current. And one of the ways that I'm sure Mauro taught you guys like that, because that's how he taught me when I was a grad student with him, is to think about how much these species have to travel, right? So if you have a very thick diffusion layer, there's no material on the surface, and material has to travel from here to here, right? So remember, he talked about that, I'm sure, on the scan rate kind of coevolution of current. So the thicker the diffusion layer, which would be in his parallel, I don't get confused, but parallel to his talk, would be when you have a slow scan rate. here the material has to travel further from solution to reach the electrode, so my current is going to be smaller. If my diffusion layer thickness is quite small, material is right there, so like it can reach quite easily, so my current's higher. And that does explain, and that's why you have, if we go back, that's why I have an increase in my P current here, right? It's just because of the fact that I'm compressing the diffusion layer. One way that I prefer to see that, and that's just my mind, like you guys think as once, that the driving force for the diffusion, and I'm saying quotes because there's no driving force, it's just Brownian motion, right? It's just statistics, but the rate of diffusion is proportional to the gradient of concentration in a sense. So that's why I'm taking that liberty. So the steeper the gradient here, right? So the thinner the diffusion layer, you have a massive change of concentration in a very short span. So that's a very steep line. Reactions happen fast. And you can think about like a ball rolling here, right? Like it's going to roll this hill much faster than if it was here. Thicker diffusion layer, same change in concentration, but in a very large span, you have a much more gentle and gradual steep there. So the reaction happened a little bit slower, right? So that's how I like to think and to understand what's going on and why the currents are different. The fact that the current on my reverse sweep is smaller, I'm pretty sure we finished that. Like we all understand it's just because I'm consuming the material. But why the current increases here is not because I'm increasing the concentration at the surface, because the concentration of ox is fixed in a sense, is 10 millimolar. I cannot produce more. I cannot produce more than that. It's because I'm compressing the diffusion layer. I'm leaving material close there because there is a reaction. So instead of the electrochemical reaction here, where I have this large diffusion layer, because now red can travel freely and I'm consuming a lot of ox, because I have a reaction right here that's regenerating ox, it regenerates right there in front of the electrode. So I compress my diffusion layer quite a lot. By that, I make the mass transport more efficient, and hence I increase the current. And that's how I tie together that to this kind of micro electrode or UME profile that we talk about, is because UMEs, they do have a much higher mass transport rate. Like mass transport to them are much more efficient. And part of it is the diffusion layer size, and part of it is diffusion layer shape. So it's more like diffusion layer shape. So maybe a more fair comparison to that, it's not a UME, but it's a rotating disk electrode, which I know Mauro haven't talked about, but I know a few of you guys know about. It's an electrode that's we call a hydrodynamic voltammetry if we're recording a voltammetry. So instead of only relying on diffusion, we actually spin the electrode. And by spinning, we actually kind of suck solution towards the electrode. So I always bring the material. And the consequence of that is that I go from if it's stationary, a thick diffusion layer, to a very thin diffusion layer, and hence I increase the mass transport. And when I increase the mass transport, I have a CV that looks like a steady state one, right? So I know that might be confusing, but the point that I want to come across here is that it's depending more on the thickness of the diffusion layer than in the surface concentration, right? What explains that the reaction happens faster because I'm compressing the diffusion layer. There's a question here that I don't quite understand, how it's connected to reaction BL thickness. Is BL the boundary layer thickness? So the reaction is happening all over here, and the way it is, if I understand your question, I'm sorry if I didn't, the way it's related to that is that the thickness of the diffusion layer and the boundary layer thickness is going to be tied together with the rate constant of my, well, again, interplay rate constant of the chemical step and scan rate, which I think is the next slides we're going to talk about, right? So the slower is the chemical step, or the faster you scan, you afford less time for this regeneration cycle to happen, right? Again, affording less time to this reaction, so you have a different in your boundary layer. I think Tiago asked if you like. Okay, fair enough. We can discuss later. If I didn't reply at your satisfaction or I didn't understand, we can talk about it later. So let's, in the interest of time, I would talk, it's related to the GIS talk. Yeah, okay, so maybe it's the fact that I'm missing GIS talk, but if I understand what you're saying about boundary layer, the boundary layer maybe on the simulation, fair enough. There's no boundary layer specifically here for the simulations for the reaction. So you can ask him about more on console, but I'm imposing a boundary layer on the simulation domain. So I have an equilibrium reaction here. So I still have a boundary layer here for the Baltimore kinetics. Same thing, doesn't change at all. But remember, we're solving that Baltimore kinetics equation. A big part of it is what's the concentration on the surface of the electrode. So I'm just imposing here like a boundary condition that I have an equilibrium reaction happen in bulk solution. And that equilibrium reaction is this one here. right, with a constant that I give the value of simulation. So we'll impose a domain kind of boundary, like it's a boundary condition, not a boundary layer, sorry. You impose a boundary condition to the entire domain, which is just going to change the overall concentration. So instead of only by diffusion the surface electron, I have this implementation. So this is essentially the boundary condition for those simulations. Oh, as I mentioned, and I'm just move on, just for interest of time, happy to talk more about that, is there's an interplay as well about the forward rate constant and the experimental time rate. And same thing, same reasoning. Let's think about half-life. Let's think about affording time for this reaction to happen. This process happens quite fast. This process in this case is going to be a little bit limiting. So if I scan my potential quite fast, I'm not giving enough time. I'm not allowing this KF to act upon my system. So I'm pretty much have a reversible system in a sense, or I have a lesser degree of the electrochemical cycle manifested. If I scan very slowly, it takes me longer time to flip that potential to reach that condition that I reduce stuff, meaning that I'm allowing ample time for this KF to take action, meaning that's just going to consume a lot of red and produce a lot of ox, right? So it's just the same thing as the EC1, 2, or ECX mechanism, but it's just the fact that now I'm affecting both peaks, right? That's one way I like to see. This graph shows that for different scan rates, and we do have a capital K dimensional constant for the system as well. I just don't think is the most pretty one or useful one to think. I prefer to see in scan rates in this case. And we have 4 different scan rates. And as I said, this lowest scan rate, you have a nice duck-shaped CV. If you go very fast, you don't have anymore. Caveat to this, of course, that look at the CV, and you see again, I'm trying to normalize somehow. I'm not going to ask you guys why, because I think that might be a little bit of a curveball. And also, it's a segue for me to talk a little bit about EC prime better. But here I have the EC prime current, so it's the current of the system with R in solution, against the current of the system without R in solution. So if the simulation is easy, I can either set the concentration to 0, or I can just go to console and just knock off a button and say, yeah, don't think about chemical reaction. But that's the beauty of the EC prime, and that allows us to study, right? So the same way that I talk about studying those reactions with EC reactant CV, the EC prime, remember, this doesn't happen spontaneously, right? This is an electrochemical reduction. This is a chemical oxidation. I need something to change electrons of my species. So it's not going to change electrons out of the blue, right? It needs a species in solution to react with to change electrons and to be reoxidized. So it allows me to control a switch, an on and off switch. And it's not only an off, right? It's not only a binary state. I can kind of control the extent of the reaction happen, but I can run the experiment without R in solution, and I can get all my diffusion unlimited currents. And then I can run with R in solution and get all my catalytic current as well. And then I can normalize them. And this is going to allow us, I'm going to talk about in the telltale part, that this allows us to investigate the system a little bit better and get more information about it, right? But I think it's fascinating, or it's important to know that we can actually flip on and off. So it's not only an artifact of my simulation, right? It's not because, oh, Gabriel has a computer, he can turn it off. Like you guys can too if you're on the bench, right? You can just go there and not put in solution. And all is good. You just have the electrochemical step. You can actually turn on and off this chemical step. So as I said, if I'm going very fast, I just have diffusion limiting step because, yeah, that's it. I'm just diffuse limited by this guy here. I don't afford time for this reaction to happen. If I go a little bit slower, then yeah, then it's a kinetic control kind of thing because this reaction happens so fast, and that's the limiting step. And then I have this increase in current because of the squishing of the diffusion layer. I have this plateau because also is a higher efficiency mass transport regime, right? And again, bear in mind, this depends, right? There's a ratio between the voltammetric scan rate and the KF. If my KF is very, very high, in order for me to see a reversible system, I'll have to scan very, very high. And we go back to the caveats of CVs that maybe you have a lot of capacitive current, for instance, and that's a problem for you. Well, applications, I think it's interesting for us to talk about applications for the cycle, and we're going to aim on analytical, right? And this is a slide, by the way, that I definitely took from Thiago's talk, that it's interesting for us to think that I have an amplification of signal, right? So if we just go back, we have a decrease of signal here on my reverse, which is fine, but I have a massive amplification of signal here, right? So it should be very small, the current, and I'm just amplifying quite a lot. So if you think as an analytical chemist, I have a lot of advantage on that, right? I'm able to detect stuff that maybe the current was too small, maybe it's near the signal to noise ratio, or even if it's not, getting a higher signal is always an advantage. And the classical example for that, let me just go. is the glucose sensor, is the first glucose sensor, right? Here, it relies on two catalytic circles in a sense, but just based on the redox cycling of arsine over the electrode and the fact that I have the glucose oxidase enzyme that can do an EC prime reaction with it. And what drives that EC prime reaction is the presence of glucose, right? So it's just, this is a very old CV because this is a very old technology, by the way. But you can see in the absence of glucose, you have this very ducky shaped small CV. And then as soon as I add it, I have this plateau and a massive increase, right? So electrocatalytic cycles, EC prime reactions, they are very, like, as an electrochemist, they're interesting to study, of course, but they find a lot of use in the analytical science because you have an amplification of signals. So always bear that in mind. And if we have time, we might talk about how we can use that in a different way. And maybe it's just me trying to oversell something that I did back in the day, but I thought it's a neat way to look at those systems, try to use them as an analytical tool, but kind of flip the coin if you cannot use it in the proper way. But bear that in mind, you have this massive gain in current. So it's a very nice analytical application because you're increasing your signal. Telltale signs of an EC prime reaction, well, there are a few of them. The first one is that the ratio between the backward peak and the forward peak, it's much larger than one. And this is because one of them were decreasing quite a lot and the other one were increasing quite a lot. So telltale sign, that's a EC prime. Same caveat to scan rate again. Remember, it's tied with the KF. So don't record only one CV and take your conclusions. And especially for negative kind of diagnosis. If you run a CVO, it's not an EC prime because I don't see this massive ratio. Run different scan rates, and then you see if you run one scan rate and you already see that's kind of like a positive diagnostic. Decrease with E peak forward over the scan rate also. More importantly, I think, and that we're going to mention that might reach limiting, the forward peak might reach the limiting case, as we saw, and that limiting case we can mathematically define, and it's quite similar in a sense to a microelectrode kind of thing with another term here for the concentration of R. My forward peak is much larger than the predicted Handel-Savic equation. So I think that's the best diagnostic tool you can have, right? You can calculate and see, oh, that's not a diffusion limited process anymore because I wasn't expecting to have that. And if you want to get quantitative values, for instance, you can have the ratio that I talk about. So the E kinetic here would be the EEC prime. So you can run your reaction with R in solution, run your reaction without R in solution for different values of V, and then you can actually find the value of K, right? So if you have, especially if you go to low scan rates, you have this plateau kind of behavior, and you can just divide it, for instance, the Reynolds-Savic equation here, and then you just get a relationship for your KF that relates to V, right? So that it is an analytical tool in a sense, the CV, although, as I said before, I much prefer as a kind of diagnostic to a qualitative kind of thing. Well, what if R is not in excess, right? And here's the area, because I'm going towards the end and towards a different mechanism we're going to talk about, that in my opinion, it starts to get a lot like reading the tea leaves, right? And we're going to mention why, and we're going to mention alternatives. So that's why, again, CVs, very good diagnostic, very good to see the reaction and actually to have like kind of a profile, a shape, but it gets tricky. Like it is a very dense subject with a lot of nuance, right? So don't expect you to just jump in the bench and just say, okay, this is AC1, that's an AC2, or that's an AC prime. There's a lot of nuance. It's hard to characterize those reactions because of things like that. So what if R is not in excess, right? It's not entering the amount of R. Well, that's the CV that you get. Would you guys expect for the single step process to have a 3-peak CV? If you guys want to type just yes or no, just type yes or no. But I do think it's quite amazing that for just a simple electrochemical step there, we have 3 peaks. And of course, I'm always asking you guys, but I'm taking this opportunity always to drink something because it's a nice technique to do. No, oh, no one's answering, but I don't know. I would say I wouldn't expect to have a 3-peak. And why do we have 3 peaks if R is not in excess in a solution? Remember, if R is in excess, I have this nice 1-peak CV. I have this nice plateau if it's low enough scan rates. If R is not in excess now, I have this weird shaped CV. Well, once more, we can resort to our good old friend concentration profiles. And I know that EC primes, I tell you guys to look at the diffusion of the thickness, but in this case, that R is not in excess. The concentration profile over the surface of the electrode is going to be quite informative. So now we have red, it's not in excess. So now it participates. Now we can see in the graph actually. So you can have a look here. You can already see that it's a very small concentration compared to my 10 millimole, right? It's 2.5, it's a quarter of it. And you can see that it fades away quite quickly. It just goes to 0 quite quickly, right? So I do have one peak here. That's my catalytic peak, right? And a telltale, that's the catalytic peak. Remember, all those CVs have a negative peak potential here because of reduction process. Look how positive this peak is, right? Remember of Lechter principles that we talk about. Remember of me shifting that equilibrium towards making easier. So the action of that small amount of R here is just shifting this equilibrium until I run out of R. Once I run out of R, my catalytic cycle stops and everything behaves just like an E reaction. So that's why I have a first peak, which is a catalytic current, and then I have a second peak, which is my normal current. So as you see, it gets tricky. And if I just increase a little bit the ratio of R, this peak starts to go a little bit larger. I start to shift more positive. I start to decrease this peak as well. The ratios change. So those could be diagnostic tools as well, but it's quite tricky. And we're going to talk about a paper that tries to investigate those things a little bit better. So on those aspects of reading the tea leaves a little bit, I'd like to present the final mechanism we're going to talk about, which is the ECE mechanism. And by now, you guys realize that we are not creative at all as electrochemists, right? We're just stacking letters. And that's exactly what we're doing. It's just an electrochemical step, followed by a chemical step, followed by electrochemical step. So in a sense, this is similar to the EC prime mechanism with a flip on it, which is I have my chemical step here, right? And now I'm putting a lot of the potentials here. I'm stressing them out because I think they're going to be quite useful. So I have this chemical step, this reduction. I have a following, this electrochemical, sorry. I have this following chemical step, again, forward constants, backward constants, equilibrium one. But the product that I generate somehow, and again, this case, let's think about decomposition. Let's think about reacting something in excess, for instance. No, sorry, that I went totally the wrong way. So I have a product P, and this product P actually is electroactive as well, right? So remember on the EC prime mechanism, I promote X, which was electroactive as well, but then I'm just cycling here. But imagine the P can also undergo a reduction. It's a different process with a different potential, more cathodic, for instance, in this case, right, of E0. Would that change the profile of my reaction? Yeah, Paul, yeah, we'll have another peak again. That's a very good guess, and it will. So that's a CV, for instance, that I run for a given KF, which wasn't particularly fast or particularly slow, it's kind of mid-range. And yeah, we'll have another peak. But one thing they're going to stress out already, we also had another peak when the EC prime wasn't, I didn't have our nexus, right? So hopefully now you start getting how this is a little bit reading the tea leaves, how it's hard to get nuance on all those mechanisms. So yeah, I would have, because now I have then my reduction of here, actually, this is actually for a fast escape forward, sorry. I have my reduction here of ox. So ox is going to red, all right? So Denuault is the first peak, is the reduction of R, blue line decreasing. Okay, so going back here, is that? Okay, so I can go back to that again for this question because I think I ignored it. Yeah. Okay, so before we go to EC, sorry if that gets confusion. So the first peak is not a reduction of R. R is not electroactive. This first peak is the reduction of ox, but it's the catalytic process of ox being consumed by red. Remember that I'm recycling ox here by action of red. So as long as I have red in solution, I'm producing more ox. But more than that, remember to the first slide, I'm shifting the equilibrium because this reaction here consumes red, right? So this is the main equilibrium that I have, is my electrochemical equilibrium. If I'm removing red from solution by action of R, I'm facilitating this process. So you expect this reduction to happen at less negative potential. So you expect it to happen here. Okay, you got it, right? Yeah, and that's it. So that's the point where I get zero. As soon as I finish R, then this catalytic cycle finishes. I have now catalytic one more, and this becomes just an electrochemical process. And because R is not in excess, because I still have a lot of red in solution, then it just follows to as a reaction. Okay, thanks. I'm good. That's clear. So just recapping then, Paul, I think, said here, yeah, that 2 peaks. Yeah, he's right, 2 peaks. And if this is a fast reaction, I have my first reduction here of ox to red, then chemical step, very fast, just consumes every single bit about of red to produce P, which turns out to be electroactive as well. So if I swap my potential negative enough, now I start reducing P, right? And it's just a normal CV. And then I'm going back to O, because now I flip the potential. Now I'm producing O. Now I'm reoxidizing O back to P. But remember, we assume that this backward constant is always 0, or just to make our life is 0. So I never produce red back, so I don't have the reverse peak anymore, because I just have now this process. So I have the reduction wave of the first process Then this reaction consumes every single bit of red that I produce to produce P. And now P is a reversible system, is diffusion limited. I'm just going to have a nice CV from P now, right? So that's the ECE mechanism in a sense. But there's as well, I forgot that I have this mark in here. So the reduction of ox, reduction of P, the oxidation of P, right? Surface concentration profiles might help us understand a little bit, and it gets very confusing in a sense, but you can see that, first of all, I kept the same potential windows for the simulations because I think this highlights quite a lot the Denuault principle kind of thing. You can see that in the other ones, if you remember, it took me a long time until I start reducing ox. Now, because I have that couple system, that's just Denuault principle, just shifting the equilibrium, straight away I start consuming ox, almost straight away, right? Red, you can almost not see here because this kinetics is quite fast, but you can see that P follows very well ox, and that's just because this kinetics is fast. I'm just producing a lot of P as soon as I produce any red. As soon as I flip the potential cathodic enough, I start to consume P again and produce O. So it's a little bit messier of the profile, but I think it explains why we see those peaks. Examples of those, plenty, of course, again, just stressing out how usually is the nature of the molecule that's a little bit more complex, but this bipyridine complex here, there's the nice thing that, is it possible? Sorry, I'm just reading the chat. It's possible to have different oxidation according to many different reductions. I'm not sure I understand, but usually of those processes, what you can have, if I understand, usually is a one-to-one kind of thing. If you're thinking about all those processes are electrochemically reversible, right? So they're diffusion limited. So we're always going to have one oxidation to one reduction happening. What we're seeing here is that the action of those constants is just removing them solutions and essentially making them irreversible. So again, if I'm understanding, so remember that this first process here, it is a reversible process, right? So you're expecting this to have another peak here, but because of the action of this constant here, I'm just making this process reversible because there's no red anymore in solution. And then I have just the second one. So although we used to be a one-to-one, have one reduction, one oxidation, I don't have anymore. And it could be the case that I have a one-to-one, and I'm going to show this on this example here. So again, think about scan rate related, right? It's all about scan rate. It's all about the time this constant. It's all about how long I afford this constant to act upon it. So even if this is really fast, but I cycle really fast, I'll never see this step. So that's an example of this bipyridine complex here, which can undergo a reduction. Then it can go a chemical step here, which becomes another species that actually can also go a reduction, right? And again, I took that from Compton's book. I think it's a reprinting for a paper, so my bad that I didn't reference the paper here. But those are CVs for this system recorded at very different scan rates. Just by looking at the amount of peaks that I have, and maybe the potential shift a little bit, could you guys guess which one is the fastest scan rate? So just put in the chat, if you will, is the fastest scan rate A or the fastest one is C? E, sorry, not C, yeah, E. Okay, so Paul's saying that the first one is the fastest one. There's more people saying the E one, the last one is the fastest one. Okay, so let's see. The fastest one is E1, right? And people that are saying E, you guys are quite on point. And again, it's just here I see only one process, right? So we don't even need the reaction, have everything here. If you look, this is the first step, right? So the only thing I have in solution for startup is this thing here. This guy can reduce, all fine and dandy, right? But also this product can react if given enough time to produce another species that also can reduce. If I scan fast enough my potential, which means that I'm not only going forward fast enough, not only reducing, but I'm flipping back to oxidation quite fast, I don't allow this reaction to happen to a large extent if it happens at all. So the only thing I have is this first step here. So if I only have one peak, one reversible peak, I'm just reducing the species and coming back again because I'm doing that process so fast, I'm flipping the potential so fast that I never saw the chemical step happen. Now, if I decrease the scan rate, if it takes me a lot of time to reduce and then go back to the potential, I'm affording a lot of time for this reaction to happen. So as soon as I start to decrease the scan rate, you can see that I start to see a second process happening more than like a larger potentials. I see that the process starts to be larger and the fourth peak for the first one starts to be smaller. The reverse peak for the first one starts to be smaller, sorry, and gets larger and larger and gets larger and larger to a point that I don't see the return. I only see the forward process. So I'm only reducing this guy here. Bear in mind, flipping of the here is minus current, so it's all flip. So I only see the reduction of the first step. Then every single one of those molecules is converted chemically because I'm allowing enough time to this molecule here, which reduces once more to this species. It's a reversible process, the electrochemical one, so it's reduced back, but the chemical one is not, right? So it stops right here. So that's why I don't see the reduction peak back again. So as I said, tricky because you can have multiple peaks, you can have other products. You never know. It's a complex molecule. Maybe it has a other chemical reaction that couples to another electrochemical reaction, if you may. So we are not creative. You can always stack letters. You can have ECEE, ECEC, just like go crazy, be creative. Anything can happen in that sense. And that just boils down to chemistry, right? If the molecule can actually be electroactive or not. So what if the kinetics is lower? And that's me hammering the point that it starts to be a little bit reading like the tea leaves, right? So this is a CV quite similar to the other one that I did, but it's just the fact that this, if we're using this system, for example, this constant, the chemical constant, it's a little bit slower, right? So now we can actually see the concentration of red. I have to rescale, but it has an appreciable concentration now that you can actually see. But you can see that if I compare this graph to overlaying the EC prime that I show you guys when R, the reactant, was not in excess, they are very similar indeed, right? Like one peak is more than the other, one peak is a little bit more or less cathodic than the other. So things getting really complicated. And that's the point that I like to make, that it's not easy to look at one of those systems and decide what the mechanism is. Right? You have to stack the cards in your favor, but we have other alternatives that I'm going to talk about. But I don't have a telltale sign slide for ECE mechanism, just because I think it's very hard to. There are a few telltale signs, but the best thing to do is, well, first of all, to see if it is a known system. Is that unknown? Well, it's not in your favor. But a few things to do is expand your scan window, right? Go near the limits of your solvent breakdown, because those processes, like they happen at different potentials. Here it shows the potential to be very close to one another, but you can see the real world, they differ by quite a lot, by 800 millivolts. So first thing first, if you see a CV like this and you have a suspicion that your species is not stable and might be able to convert to something electroactive, and the only way you have your suspicion is to know your molecule a little bit, like is to do your chemistry homeschool. So if you see a CV like that, just expand a little bit the window, see if there's another peak popping up, and you can try to understand if it's an ECE mechanism. So it's not easy, especially ECE, and if you start stacking, just bear in mind they do exist, but it's also not that easy, and that's why I said tea leaves, reading tea leaves. That's just a fresh paper that was received in August, was published in October, but we just had this conference, the further discussions, and that's one thing people are doing nowadays, right? They're trying to do neural networks, they're trying to do artificial intelligence to try to understand and try to visualize and characterize all those mechanisms, those processes. So essentially, you just train the network with a lot of simulated data, and then you just take your CVs and you just throw in this neural network, and it tries to classify for you, because it's going to be much better in getting those nuances. Like, look at the difference of those CVs. Although they look different, it's quite hard for us to hammer down what's the process just by looking. Right? So it's going to be much better. And the thing they did here, people have done that for a while now, but they're just including now more cycles, the second, third cycle, and seeing that it helps a lot the AI to classify those mechanisms. One of the other things you can do, and the thing that I'll suggest, and you guys are learning with Guy, you simulate your system. Like if you have any kind of suspicious, simulate your data and try to compare them. If you want anything more to understand all those systems and to other techniques, because it's just a brief overview that I gave to you guys, and just say there's a lot of it's quite dense, a lot of nuance. I strongly recommend this paper. It's also relatively new. I think it's from last year or this year. A lot of great people here as great electrochemists, and they try to do like a guide to reaction mechanisms for synthetic chemistry, right? Because synthetic chemists are the ones that are going to make those weird molecules. And I say weird, I'm sorry if anyone is, because I'm an electrochemist. I always play that I do salty water electrochemistry. I do all behaved stuff. But if you face with those problems, there is a lot on this paper that helps you understand and which technique you should use, what are the relationships, how do you calculate constants, what's the ratio of the current peak with scan rate that gives you the kinetic constant, the forward rate constant. Everything's in this paper. I strongly suggest. Just so I don't tell you guys that, and I'm not just putting everything into that paper, but there are plenty of techniques in electrochemistry that you can use, plenty of them that you can investigate. This is from Bart's book as well, which I strongly recommend. There's considerations of all those techniques, so we could use any one of those to investigate a couple of reactions and reaction mechanisms. Bear in mind the same mass transport aspects are problematic, and that's why you always have to calculate. Remember that interplay between scan rate and kinetic constant. You need to calculate the temporal parameter for those stuff. You need to see if your technique is able or not to get. And just go into a simple case of the CV. If you have a very fast K4 that you need to scan at 10,000 volts a second, you're most likely not going to be able to see that reaction of a CV, right? Your capacitance current is going to be massive. You might resort to fast scan voltammetry, which is a little bit reading to lives as well, to be honest. So choose another tool. Is there any available software to upload? Not that I'm aware. I know that Alan Baum's group, and especially Ji Zhang, I think the students between them, they haven't uploaded yet their code to GitHub. They will. It's not going to be a software for sure. I think it's a Python script. So there is an energy barrier there that you have to learn something. But until now, there's no software that you just upload. Give it 5 years tops, there definitely will be, right? This is definitely a growing field, especially because if you think about energy conversion, storage, and all those reactions, it's not only classifying reactions, but there's a lot of people working in AIs to classify catalysts, for instance. What's the best catalyst for, hydrogen evolution, for CO2 reduction, or whatever. So there's a lot of driving force in that field that people will be inputting, and you're going to see at some point softwares coming out. Now, the only thing you can have is go to those papers, find the SI. It's definitely going to have a link to the GitHub. I just know that they haven't put yet because I was at this conference. We asked them about it, and they said they are still refining the code, cleaning up a little bit because sometimes it can get messy, and they will upload in the GitHub. And you're probably going to find on the SI, the correct version of SI, because those papers are still under correction, or on their website as well. You can visit both their websites and should be fine. Also, I know because this is in this maybe the 10th tangent of the day. Every time you find something like this, find the first author, either email them, or nowadays, we're even talking to Thiago, tweet them. That's why I put in my presentations Twitter. You can always find those people on Twitter, and they're very helpful. So yeah, pick your weapons, horses for courses. There's different techniques, but bear in mind, it's a very deep, it's a hard field, full of nuances and very dense. And yeah, we don't have much time, but just to show, and again, it's me overselling the thing. It's just the fact that you can have different mass transport rates and microelectrodes, which you guys didn't saw much, but because of their diffusion profile, they're not great at EC prime mechanism, right? Because material doesn't stay long enough in the surface they do react in solution, but once they react far away from the electrode, right? So you can never see the catalytic aspect, or it's hard to see the catalytic aspect. So one way we explore this is to actually using a ring disc microelectrode. And instead of looking at the increasing signal, so this is just paracetamol, right, being oxidized here, and then the action of GSH, glutathione, is just reconverted back. Instead of seeing this reconversion back, because the paracetamol needs to be in the electrode, because mass transport so fast, as soon as the reaction happened, this paracetamol is far away, like it's not near the electrode anymore, so it doesn't increase the current. So if you put a second electrode a little bit further away, so this could be a flow cell, for instance, a rotate ring disc electrode, or in this case, in our case, an electrode, I can actually now see that signal. I can actually collect this stuff. And in this case, you can rely on the sequestering of that species. So you can think a little bit out of the box and how to use those catalytic cycles, even if the mass transport is a little bit different. And I just put this here. I don't want to go into detail because I think it's out of the scope, but just to realize that it's mass transport. So it's not only KF, the forward rate constant, and the scan rate, but also tied to mass transport, like things need to be. So it's much more tied to the mass transport rate than anything else, which you can play with the scan rate as well. So bear that in mind and see that horses for courses here, but there are things, and Guy's not listening to the talk today because he has a meeting, but he's going to talk. Guy has, I think, 4 or 5 papers on reaction mechanisms with ultra microelectrodes, which they're brilliant. But again, there's a limitation there because microelectrodes have their fast mass transport, which can hinder the application a little bit. With that, I'd like to finish before I go over my time. Those are some just nice references besides that paper, those 2 papers that I showed. Those just like some nice references, a few of Guy's papers as well. And I'm happy to take any question that I might be able to answer.
Thank you, Gabriel, for the amazing talk. It will be a great day for simulations today. Thank you very much. It's a clear presentation and good, with good slides, good examples. You improve a lot the class. Thank you very much for that.
No, no worries. I'll share it again. I think there's a comment here. My goodness, if these can get really complicated. Yeah, they can. And I sometimes on electrochemistry, and I think Thiago will know that because I'm quite talkative, as you guys can see. So I talk to a lot of people. I'm kind of an old man in a young man's body. So I talk a lot of like old professors and get the history behind. If you think that CVs are complicated with chemical, like with this couple reaction, as soon as you start adding as well all the surface process adsorptions and stuff like that, things are really messy and everything becomes reading the tea leaves really to the point when people used to do platinum electrochemistry, they have to be careful with adsorption to a point that people don't use deodorant. So depending on the soap they shouldn't use, things were complicated. And most of those things were simplified by simulation. And I'm going to advocate towards COMSOL just because it's the one that I use quite a lot. But there are other packages for simulating. But if you think that all those processes happening, they are quite well behaved. So mass transport is very well behaved and easy to simulate, right? That's not a big deal. That chemical equilibrium is very well behaved and fine to simulate as well. Absorption as well, we have nice models that overcome that and can describe absorption. So if you have powerful enough computers that can put everything together, then you start to not reading the tea leaves anymore. And that's why simulations are in place, because you can make assumptions of your system. You can describe mathematically fairly accurate all those processes by itself. And then you can put on a FEM, like a finite element method modeling, for instance, and you just can see how those things play each other and what's the experimental outcome. So I'm definitely, I know that people don't need to be simulation experts, but I think now with those softwares, and he's going to talk about also Oliver's, which is a friend of ours, he's from a student, has a free software. There's so many tools, free access now, that I would recommend people to demystify how to do simulations and definitely dig into that because it helps a lot. Caveat of that, you can always feed the data if you want to, right? You can always, so don't simulate without any judgment. You're still the chemist behind the wheels. So take your best chemical judgment and simulate those aspects.
It's good to highlight that. It's impressive because the people normally have fear to use simulations, and there is easy softwares now to do these and more friendly, like to put like this. Thank you very much. Yeah.
No worries, absolutely. I don't know if you know, Thiago, if still remember that there was a free one from was Biologic or something like that. I don't know if they still have it, but it was a nice software to run simulations, at least, and it can do EC, I think.
EC, yeah.
Yeah.
It's possible to simulate. Normally I use in the classes for the undergrad students. Yeah. It's an easy one, and there's a free version. Yeah. Let me check if you have more questions here, but a lot of people doing congrats for you, and people are really impressed with the number of the discussions and number of examples that you put in your lecture. Thank you very much, Gabriel, for that.
No worries, guys. Thank you, Thiago, for the invitation, and thank you everyone attending for the participation. I know it's hard, it's virtual, but I like you guys engage quite a lot, and I think that's important. I think that's how we do progress.
This is good to put the school on track. Yeah.
And tune in for tomorrow. Like tomorrow, we're going to talk about stuff that's a little bit different. We're going to mention that interface again, like that electronic interface. We're going to focus more on almost, no, not all. Sorry, I remember the slide. So we're going to focus on both reactions, heterogeneous and homogeneous. But hopefully, I'm going to show you guys how much of a pain that heterogeneous interface can be, but also can be a joy that we can see some different stuff, some nice stuff.
Thank you very much, Gabriel. And there is Ashley saying thank you for the insights. These insights are good. This is the idea of the school, to put the insights. Yeah, I would like to request you to stop to share your screen.
Oh yeah, absolutely.
Because I only do an announcement until the break, and it's important only to highlight this.
Stop sharing. I'm saying that sometimes I'm an old man. Okay.
Thank you.
No worries.
It's only to remember that tomorrow it will be the last day of the school, and I will miss a lot this moment since it's important for all of us to try to put the school to discussion, this electrochemical discussion. And I would like only to remember that tomorrow, for the participants that are here in the Zoom room, we will have a raffle of an ebook tomorrow, and please stay in the closing ceremony. And after the closing ceremony, we'll take a picture of all the participants and stay here in the closing ceremony. And now we will have the break. We will have a 15-minute break and see you in 50 minutes. Bye-bye. Hello, everyone. We are back for more discussions and more discussions about simulation and for the amazing simulations that Guy normally always show to us. And I will not introduce Guy again. Guy was already introduced. He is with us 2 days consecutively, and we'll miss Guy now because we will. It's the last day that we'll have Guy here. I hope that Guy could be with us to take a picture tomorrow. And Guy is with you now. If you would like to share your screen.
Is that working?
Yes, perfect.
Right, so I'm just turned on the chat. So, right, hello everybody. Good day, wherever you are. So this is the third of our series of lectures on modeling. And we're going to take a step up today. I want to show you what we can do with more complicated electrode geometries. And for that, we're going to work with finite element method, and in particular with a software called COMSOL Multiphysics. So as we did for the previous lectures, if you want to type your questions in the chat, I'm keeping an eye on the chat at the same time, so I'll try and answer as we go along. So here we are. These are the topics that I want to cover today. We're going to look at different electrode geometries, and we're going to see how that introduces different partial differential equations for mass transport. I'm just going to focus on diffusion. Later on in the lecture, we'll look at other forms of mass transport, including migration and convection. With the difficulty of simulating complex geometries, we're going to introduce the finite element method and compare it briefly to the finite difference method. I'm not going to go into great depth into the finite element methodology. As I said yesterday, I'm not a mathematician. I would just give you the basic idea of the method. And I want to show you how we can exploit that by implementing our models into the software called COMSOL Multiphysics. And we're going to look at two examples, the simulation of the voltammetry to a microdisc electrode, which is purely diffusion controlled. And then we're going to finish with the simulation of a channel flow cell with a microband embedded in one of the walls of the cell. And we're going to see how we can exploit the finite element method to really understand how the concentration profiles develop within the channel. So this is going to be an example where we combine diffusion and convection at the same time. So without further ado, these are the geometries I want to consider. We're going to look at spheres and disks and bands, and then electrodes with no symmetry. I just want to show you how we can handle these and how we can simplify them. The basic idea is that I want to show you how the partial differential equation for diffusion changes when you change the geometry, and how we can simplify this. Because as you will see, the coordinate system will change, and we have a choice sometimes of simulating this in 1D, 2D, or 3 dimensions if we can't make any simplifications. And what I want to do with these different geometries is to start introducing the different boundaries that we need to consider. Until now, I've only considered 2 boundaries because we've done simulations in 1D. So one boundary was the electrode, the other boundary was either the bulk of the solution, or in the case of the battery, it was an inert wall which was facing the electrode. But you will see today with these complex geometries that in fact we can have different kinds of boundaries as we go around the cell domain. So I'm going to start with the simplest of all, which is the sphere. So now you imagine that your electrode has the shape of a sphere. The center of the electrode is the origin of our axis, but the electrode is actually sitting at some distance away from the center, and that's the radius of the electrode. The partial differential equation for diffusion in spherical coordinates is a little bit more complicated than what we saw for planar diffusion. So we now have two terms. The left-hand side is the change of concentration with respect to time. Here, I will be one or the other species. And we have a second order term here, and we have a first order derivative term, but we have a 2 over r there. So it's a little bit more complicated. It's a little bit more complicated, but it's still one-dimensional. We can afford to simulate this problem according to the radial axis, except now we need to be aware that the electrode sits at some distance rs away from the center. So our initial condition, well, is basically the same, except that now instead of having x equals 0, I've got to say that x is the has to be greater than the radius of the sphere. Now we have two boundaries. One is on the sphere surface, and here I've selected the same sort of boundary condition as before, which is 0 surface concentration to drive a diffusion control process, and then equal in opposite fluxes. And then far away, when the radial dimension is infinite, then we retrieve the initial condition, and this is our bulk condition. Now, what I want to emphasize as I go along the different geometries is the way we're going to calculate the current. This is going to change as we make the geometry more complicated. But for this one, it's still fairly simple. It's just the usual constant times the flux, and the flux is the gradient of the concentration at the electrode surface. So the way to calculate it is very similar to what we did for the planar electrode. So as far as I'm concerned, the sphere is very similar to the 1D problem for planar diffusion, except that the partial differential equation is a little bit more complicated. So if you wanted to do this with explicit finite difference, which is fairly straightforward, you would have to have another term in your explicit finite difference expression, and this other term would have to account for this. But otherwise, it's fairly straightforward, and that can be easily simulated with 1D explicit finite difference. And this is quite useful because very often we can approximate micro disk electrodes or micro electrodes in general to spherical electrodes. So instead of having to do a complicated 2D simulation or 3D simulation for a micro electrode, we can simply assume that the microelectrode looks like a sphere, and we can do a one-dimensional simulation. So that is very useful, and it's well worth starting with that. Another form of electrode that we need to consider, it's the cylinder. So you imagine that you have this could be a micro cylinder, so you would have a radius of a few micrometers, but again, the partial differential equation is different. We have two terms. It looks very similar to what we saw for the sphere, except that instead of having 2 over r, we have 1 over r. So again, only one dimension. So here we don't bother with the long axis. This only comes in as a scaling factor in the current. So the length of the electrode comes out as a scaling factor. The only thing we need to simulate is the radial diffusion along the radial axis. So again, it's a one-dimensional simulation, and that can be done with explicit finite difference quite readily. The initial condition, it's here I've only written everything in terms of one species, but it's fairly straightforward. You start obviously from the surface of the electrode, so from the radius of the cylinder, and you simulate along the axis. For the boundary conditions, you've got the boundary far away, so this is the bulk boundary, which retrieves the initial condition, and then you've got the boundary on the electrode surface. Here, I've set it C equals 0 to simulate pure diffusion control. The way to calculate the current is again very similar to what we did before. Is the flux at the electrode surface. So we need to calculate the gradient of the concentration at the surface of the cylinder, and we just need to multiply by the usual constants, except that now we've got L coming here, and L is the length of the cylinder, and this is where you scale for the length of the cylinder. But essentially, the response, the amperometric response of the cylinder is completely determined by the radial diffusion around the cylinder. So again, this is a geometry that can be easily simulated with one-dimensional explicit finite difference with the algorithm that I showed you before, except that because of this extra term in the partial differential equation, we need to modify the explicit finite difference scheme accordingly, but it's straightforward. I mean, you could use a central difference, for example, to do the calculation. So moving on, I'm now looking at microbounds. So these are, for example, you can make them by making a sandwich. So you imagine like two microscope slides made of glass, and then in the middle you put a thin sheet of gold, for example, and then you glue this, and then you polish it, and this makes the microbound. So the microbound would have a width of, I don't know, 5-10 micrometers, but it could have a length which could be millimeters or centimeters. So this is somewhat similar to the cylinder in that we can simplify. When you look at the actual geometry, you would naturally assume that you need to simulate this using 3 dimensions, but actually we can ignore the long axis, so we can ignore the length of the microbound. This again will come in as a scaling factor when we calculate the current. Now, what we need to do to simulate the response of this electrode is simply to consider a 2-dimensional domain, which is like, here I make it start from the center of the electrode. You see, I don't need to simulate this region on the left because this is just a symmetric of this region. So I've actually taken the simplest simulation domain that is sufficient to simulate the response of this electrode. So that's another skill that you need to develop when you do simulations. Not only you need to know what boundary conditions to apply and where to apply them, but you also need to carefully select your simulation domain, because very often there is no need to make a very complicated simulations. You can shrink to the bare minimum, and that will save you a lot of computation, but it also save you the complexity of having to, if I had to simulate this in 3D, instead of having linear boundaries, I would have 2-dimensional boundaries. They become surfaces. So that would make the simulation very complicated. So the partial differential equation for diffusion to this type of electrode is a 2-dimensional expression. So we've got now a second-order derivative of the concentration with respect to x, and we have a second-order derivative of the concentration with respect to y. So we have to account for planar diffusion perpendicular to the electrode and parallel to the electrode, essentially. So now if you look at the domain, if I walk around the blue region here, you can see that all this is solution. This is solution, but it's a symmetry axis. So we have a different boundary here. The outer boundaries here would be the bulk, if you want, condition. But the symmetry axis here has to be treated differently. On this region here, that is basically the insulator around the microbound. So this is a wall which is not electroactive. So it could have other properties, but as far as electrochemistry is concerned, it's not electroactive. Therefore, there is no flux perpendicular to this surface. Similarly, because there is symmetry here, there is what diffuses from right to left diffuses from left to right at the same time. So the symmetry axis is also analogous to an inert wall where you have no flux perpendicular to this wall. So for the outer boundaries, because this is analogous to the bulk, then you could set up the concentration values along this region. But here you have to set a no flux boundary. Similarly, on the insulator here, you have to set a no flux boundary. And that leaves us with the last boundary, which is the actual electrode surface. So here is where you would implement the condition that represents the technique that you are trying to simulate. So here I have selected, this is this boundary here. I've selected to impose 0 surface concentration as if I wanted. Can we assume that there is no current change along I? I'm not sure I understand the question. Along L, you mean? Along L. Yeah, okay, I understand the question. What you need to imagine is if you take the blue plane that I have drawn here, whether you simulate at this particular position or further down the axis along the length makes no difference. You would end up with exactly the same concentration profile. And this is why we can afford to only simulate the blue region, because it really doesn't matter where we take this. Sorry, I have to do it with respect to the camera. It really doesn't matter where. Imagine that my hand is the micro bound. It really doesn't matter if I simulate the plane of my second hand here, or there, or there, or there. It really doesn't matter. The response will be the same wherever we take that plane. So that's why we can simplify. And similarly, it doesn't matter whether I simulate this part or the other part, because of the symmetry between the left and the right. We can just afford to simulate just this small blue section, and that will be enough to reproduce the whole response of the electrode. So these are the boundaries in qualitative terms, but now if we look at them in mathematical ways, you have to be very careful to specify the relevant X and Y regions, and then for each X and Y region, you set either the value of the concentration or the value of the flux. So if I just take this example, this is Y equals 0, so we are on the bottom here. For X greater than W over 2, W is the width, W over 2 is here. So for X greater than that, I have dC dy equals 0. What that means is that the flux towards the surface here, or towards the vertical line, the horizontal line, the vertical flux here is 0. I am not specifying the flux along X. I'm just specifying that the vertical flux perpendicular to this surface is 0, and that means no. That means the electrode, this wall is not an electrode. It's not electroactive. It's not consuming or producing any species. Okay. Now, what's interesting, I've just realized that in my list here, I have missed the vertical boundary, which is, I should have another line, which is when X equals 0, I have dC dx equals 0. So at the vertical axis here, I should really set that this flux, which is the horizontal flux here, is equal to 0. Means you're still allowing diffusion in the vertical axis, but you're not allowing diffusion across the symmetry axis. This is simply saying that what diffuses from left to right is equally opposite to what diffuses from right to left. Okay, so mathematically we just replace that by a no flux on the horizontal direction. Now, what is different with this geometry, and this is why I'm spending more time on it, because in a minute we're going to look at the microdisc. What is different with this geometry is the way to calculate the current. It's a lot more complex because now you have to integrate the current density along the length of the electrode. And the reason you have to do that is because the current density in the center of the electrode is generally smaller than the current density near the edge. The edge is a peculiar area where you've got a lot of material which is diffusing from the right and from above. As a result of that, near the edge, we have a very, very high current density. You could observe that experimentally if you were, for example, doing zinc deposition on this microband or copper deposition, and then take the electrode to an electron microscope, and you would see that there's a lot more copper or zinc deposit near the edge than in the center. So when we model the response of the electrode, we have to account for the fact that the current density will be dependent on where we are along the electrode. So for that, we need to integrate dcy, dc dy at y equals 0. So we need to integrate the vertical flux perpendicular to the electrode along dx. So it's an integral from 0 to w over 2. So from the center to the edge of the microbound, we integrate with respect to dx, but the quantity we integrate is the vertical flux. So it's a little bit more complicated than what we saw before, because in the case of the planar electrode, it was an electrode that was uniformly accessible. So that means that the current density was the same everywhere. In the case of the sphere, every part of the sphere is equally accessible. So the current distribution around the sphere is the same everywhere. Around the cylindrical electrode, we have the same current density all around, which means that the cylinder is uniformly accessible. The microband is different, and it's a case where we have to use 2 dimensions. In fact, as soon as you use 2 dimensions, very often you have to use an integral of the current density to calculate the total current. Now, for the question about the position of the blue square, again, we use the length of the microband as a scaling factor, and it is here. I'll answer the question in a second. The L value is L there in the factors that we use to scale up the integral. How can you get rid of the edge effect, the high current at the edge, to improve geometry? Well, you can't really. The only way to do that is to use very, 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 very large electrodes. So if you look at an electrode which has millimeters or centimeters, there will be an edge effect, but compared to the total current, it's negligible. When you come to use microelectrodes, so in the case of this microband, the edge effect becomes very important, and that's why we need to account for it. It becomes very important because the contribution, the local current density here is a significant fraction of the total current over the electrode. So we can't just ignore that edge. Now, for electrodeposition, if you wanted to eliminate edge effects, you would have to use additives which are essentially limiting the growth of the deposit near the edge. Now, this has been developed. If you look at the I think it's called the Damascene deposition process for copper deposition in very, very narrow trenches for semiconductor industry. They are desperate to have a continuous thickness of copper in the trenches. and they want to avoid edge effect. So they use additives which basically force the copper deposit to be uniform. I mean, the other way of doing it is, instead of applying a very large potential to drive the deposition on the diffusion control, which would create edge effect, if you instead apply a very low of a potential to try and grow this on the kinetic control, then you have a better chance of having a uniform deposition, which means you would have less edge effects. But nevertheless, as soon as you start doing electrodeposition on micrometer dimensions and sub-micrometer dimensions, it's very difficult to avoid edge effects. And the way to do that is by using additives. So it's a very good question, but it's a very challenging problem. Now, for us in simulation, is simulate it, act properly. So I now want to move to the disk, because that's one of the problems that I've selected for as an example in COMSOL multiphysics, because the disk is such a common electrode in all our experiments, in particular microdisks. And you saw yesterday in Maura's lecture, the voltammetry at a microdisk electrode is very, very different to the voltammetry at a large planar electrode. So with a microdisk, so imagine this is the disk, and this is glass on either side, and you've chopped the electrode to reveal the cross section of the wire. This would be, for example, a platinum wire, and what you've done is to reveal a disk. Now, the beauty of this geometry is that there is a symmetry axis along the z-axis here, and because of the symmetry of revolution, again, we don't have to simulate the whole domain in 3D. We can just take a cross section of the domain and simulate a 2D domain with 2 dimensions, one being the radial coordinate r and the other one the vertical coordinate z. And the arrow here illustrates the fact that we have a symmetry of revolution. So, of course, the partial differential equation for diffusion in this geometry is very different to what we've seen before. It has now got 3 terms, a second order term with respect to z, a second order term with respect to r, and then a first order term with respect to r. But again, we have a 1 over r here. So that's obviously a more complicated partial differential equation, but actually we can simulate that with explicit finite difference. Normally, I include this in my lecture to show you the complexity of doing it in 2D, but I don't have the time today. But it is doable, and it is very inefficient, because now you have to simulate the diffusion in 2 directions. So it's very computationally intensive, and this is why we don't tend to use finite difference, or explicit finite difference at least, to simulate the diffusion control response in 2D systems. There are numerical schemes which are far better than explicit finite difference. For example, the one called alternating direction implicit, which is very efficient and has been used many times to simulate this kind of problem. So that, if you were interested, you could try that. It's in the literature. There are many papers by Richard Compton, for example, where they use alternating direction implicit as a way of simulating the chronoamperometry of microdisk electrodes. But today I've decided to show you how we do it in COMSOL multiphysics, because it's a good example. Now, the boundaries here, I've listed them, but we're going to see them again in a second on the next slide. The boundaries are obviously more complicated, because if you walk along, you've got the electrode here, you've got an insulator, then you've got solution, then more solution, then a symmetry axis. So we've got all these for which we need to define either a concentration or a flux or a linear combination of concentration and flux, like we did yesterday when we had the Butler-Volmer kinetics. We had the flux of the reactant on one side, and then on the right-hand side we had a linear combination of surface concentrations. So always remember that when you are walking along the domain, you have to specify something on each boundary, and that is either specifying the concentration or the flux or a linear combination of concentration and flux. So again, we have a complex geometry, and we need to calculate the current using an integral. So this is the expression to calculate the current. So we're now going to walk along the edge of the electrode here. Sorry, not the edge, because the edge is this corner there. We're going to walk along the radius of the electrode from the center and integrate the local current density, but it's the dCdZ that we're integrating. So it's here. We integrate with respect to the radial dimension. We have to use a 2 pi RdR to account for the fact that it is a symmetry of revolution. So it's you will see later on where that is set in COMSOL multiphysics. But the term that we integrate is dCdZ at z equals 0. So it's the vertical flux at the electrode surface that is integrated with respect to the radial dimension, but using symmetry of revolution. So I'm going to go through these boundaries, but on the diagram, it's going to be easier to visualize this. So what I've done is identify all the boundaries and reproduce the conditions that we need to impose. So here again, I've selected a very simple boundary. I want to impose the surface concentration, make it 0, as if I wanted to simulate the chronoamperometry to the microdisk, the current transient. So we have now got to define this from the region where R goes from the center to the edge of the electrode, and we set the surface concentration equal to 0. When we walk now along the glass insulator, so Z is still equals to 0, the distance is R greater than the radius of the electrode. With microdisk electrode, we always call the radius A. So here we set the flux, the vertical flux equal to 0. When we walk along the boundaries here, which correspond to the solution, we just set that the concentration retrieves its bulk value. So you have to go very far in terms of R and far in terms of Z, and then you set these concentration along these lines to be equal to the bulk concentration. And then we finish with the vertical axis, which is the symmetry axis. And here you just say that the horizontal flux, so the radial flux, is equal to 0. So these are all the boundaries, all the boundary conditions that we need to set. Obviously, in the bulk of the solution at the beginning, we need to impose the initial condition. So you will see when we go through the detail of the COMSOL multiphysics simulation, we will be setting these systematically in exactly the same way we've done with the finite difference scheme. So you could do that in, well, this is exactly the same thing. You could, in dimensional form, you could make this dimensionless. So for example, to make the concentration dimensionless, well, you do the same as what I showed you. You divide by the bulk concentration, that's easy. To make the distance dimensionless, here we have electrodes with interesting geometries. You see, this electrode has a characteristic length, and it's the length, it's the radius. So whenever we have microbounds or micro discs or spheres or cylinders, we always identify a characteristic length. On the planar electrode, there is no characteristic length. So this is why I was selecting the diffusion layer thickness, which was determined by the duration of the experiment. But here it's a geometry where we have a characteristic length. Similarly, for the simulation of the charge of a battery, which I did yesterday, we had a characteristic length. It was the depth of the electrode, and therefore we could use the L value to normalize. So whenever you are dealing with a geometry that has a characteristic length, you can make all your Z and your R dimensionless by dividing them with respect to the characteristic radius or thickness of your electrode. So these are the boundaries that we saw earlier, and we could make that dimensionless if we wanted to. Now I want to shift now to the finite element method, but before we do that, I just want to finish with the finite difference, just so that we can contrast one method and the other. So the finite difference method is probably the most ancient numerical scheme that people have been playing with, because it predates computers. You could do these calculations simply by, as you've seen, multiplication, addition, subtraction, and division. And you could solve really complex problems that way. And although I showed you some very simple ways of calculating the derivatives, but there are other ways of doing it. And in fact, mathematically, they all derive from the Taylor expansion series, where you can approximate a function using the combination of derivatives to increasingly higher orders. In fact, the approximations that I use, the finite difference schemes, the forward difference, the backward difference, and the central difference, they all derive from the Taylor expansion series. So there is a mathematical background to this, and if you're interested, I encourage you to have a look at that. Now, the finite difference method is particularly useful when you are solving ordinary differential equations, ODEs, and you may have come across it in what is known as the Euler method. And it's a way of doing forecasts and predicting and solving ordinary differential equations. So it's a very useful scheme. For partial differential equations, we've seen it in the form of this explicit finite difference, but as I said, there are other ways. And generally, it works really well for 1D problems, and you can optimize it using more fancy mathematical schemes, but the finite difference method is very reliable for most 1D electrochemical problems. And you can go a long way with that method. So if you can simplify your problem to one dimension, then I would suggest you use the finite difference method. Now, when it comes to 2D, and this is why I haven't shown it to you today, if I wanted to do the microdisk simulation in 2D, it's possible. It requires big matrices, and it becomes very cumbersome in 2D. It becomes very inefficient. There are schemes like the alternating direction implicit, which are more efficient, but they all share the same problem, and it is the following: the finite difference method requires a grid, and that grid is linked to the axes that we take. So the finite difference method is not very friendly if you have curved boundaries, or if you have complicated distribution of boundaries. And this is why the finite element method is very popular, because as soon as you have a real world problem, okay, no problem, thank you. Okay, all right. So the finite element method is a completely different numerical method, and it works on the idea that you come up with trial functions which are approximations to the solution of the partial differential equations. Because they are approximations, they carry an error. And the idea in the finite element method is to minimize this error until you are satisfied that the error is within a margin that is acceptable. And at that point, you have an estimate of the solution to the problem. So in this case, in our case, it will be an estimate of the concentration in space and time, basically. So I'm going to illustrate this with the transport equation for diffusion and convection in a channel flow cell. And we're going to see this example later on towards the end of the lecture. So I wrote it here in the steady state. So the dc dt equals 0. And I'm just left with two terms. One here is the diffusion term in 2 dimensions, so x and y, because we have a channel. And then we have a convection term, which is, as you can see, this is the velocity along the y-axis. The y-axis is vertical and the x-axis is horizontal. The channel is running horizontally. So we have a concentration gradient along the x-axis, but we have a distribution of velocities in terms of the y-axis. I will show you that with figures and illustrations later on. So imagine that we have this transport equation in the channel flow cell, and we want to solve the concentration distribution over the domain omega. Omega is basically the simulation domain. It's the channel where we want to flow the solution. And there will be, for example, a boundary condition on the electrode, no flux on the walls, etc., etc. If the concentration C, which is what we are trying to find, satisfies equation 1, then mathematically you can demonstrate that it should also satisfy this integral equation where you multiply the equation of interest by some weighting function and you integrate this product over the domain, and that should be equal to 0. There are different families of finite element method, and on the whole, their names correspond to the different weight functions that people have been using to this. So the big difference is that whereas in the finite difference method, we were approximating differential terms, in the finite element method, we're going to be approximating integrals. And the beauty of this approach is that numerically, you can try that yourself using a spreadsheet, for example. Numerically, it's a lot easier to calculate an integral than it is to calculate a differential. And also, you make a smaller error relation. So there are good reasons for using this method from a numerical point of view. So how does it work? Well, imagine now that you come up with an approximate solution. I'm going to call it C prime, and you're going to substitute C prime in the differential expression here. So because C prime is an approximation to what we are trying to find, to C, then if you calculate this, there will be a residual. And we want C so that this is equal to 0, but because C prime is not exactly correct, then there will be a rest, there will be a residual. And what we need to do is improve the value of C as much as possible until this residual is as small as possible. The problem is that we can't ensure that this residual is equal to 0 at the same time, because and satisfy the boundary condition at the same time, because that would imply that we know the value of C, but we don't. So you march towards a value of C prime, which is as close as possible to C, but you never manage to make it equal to 0, because that would be having the answer. So what we do instead is we minimize this residual by multiplying by weight functions omega, and the system improves the weight functions until until the residual is equal to 0. Yes, I think the weight function is the weak form in console, but I have not explored that thing because this is going too far down the mathematical details of the console of the finite element method. But I believe this is correct. So now what I wanted to show you is one of the major advantages of the finite element method is to do with handling the domain. So omega, which was the domain in question, so this would be the channel in which I flow the solution and put my electrode. It will be broken down, and we call that meshing, into shapes. And you can choose different forms. Generally, you end up working with triangles, but there is no reason. And these forms, these shapes, are called elements. The field C along the edges of the elements. So this is a domain. As you can see, it's a rather complicated domain. This would be very difficult to do with a finite difference. And what we have is triangles. They don't have the same shapes, but each triangle has 3 nodes and 3 sides. So what we call elements are the sides of these shapes. And if we work with linear elements, so these are called linear triangles, then what we say is that the function of interest that we are trying to solve is varying linearly along the edge. So it's a straight line essentially. So you just need 2 points. The two nodes will allow you to calculate the concentration of interest anywhere you want along the edge. And then you do the same along that edge, and then you do the same along that edge, and so on. But you don't need to worry about the center, okay? Now, we can go to a higher order of elements, and instead of considering a linear triangle, we could use, for example, quadratic elements. And in that case, we would put 3 points along the edge, and you would fit a parabola. You need 3 points to fit a parabola. So you would fit a parabola along each edge of the elements. So here the axes are not involved. The domain is completely it can be shaped in any way. The equations just adapt themselves to the geometry. And the beauty of the finite element method is that it can cope with these very irregular shapes, including rounded shapes. So meshing, as you can imagine, is a key part of the building of a finite element model. It's very flexible, but it can be quite tricky to develop a mesh which is sufficiently refined to simulate the problem accurately. And this is one of the skills that you need to develop when you use finite element, is creating a mesh which is sufficiently accurate for the simulation that you want, but not too complicated, otherwise you're going to spend a long time computing. You can control, as you will see later on, you can control the density of nodes, which means you can tell the meshing routine to add more and more nodes in the region where we need more calculations. And then further away, you can lower the density of nodes because the calculations are not so important there. So in terms of electrochemistry, this is pretty obvious. Everything happens next to the electrode, and then further away, you need fewer and fewer calculations. In the same way that when I introduced the explicit finite difference scheme, I told you that it wasn't necessary to compute the concentration profile beyond 6 square root of dt, because at that point you had recovered the bulk concentration. So you're going to see that when we construct the mesh, for the finite element simulation, we are very careful to control the density of nodes in the vicinity of the electrode, and in particular in the vicinity of complex boundary conditions. And the one we saw before is where you have an electrode that meets an insulator, because at that point you have a singularity. On the one hand, you'll be controlling the concentration, and then on the other hand, on the other side, you'll be controlling the flux. Wherever you have discrepancies in the boundary condition, this creates mathematical complexities which require a higher density of nodes to compute the fluxes both in different directions accurately. There are ways of defining the mesh automatically and to refine the mesh automatically, but this is challenging, and I would not advise you to go down that route straight away. You'd better start with a very simple mesh and then improve it yourself by the general knowledge of your electrochemical problem. It's a bit of a black art at the beginning, but the more you understand about the electrochemical response of your electrode, the more you realize where the density of mesh points needs to be increased. The question, and this is where a mathematician might be able to come up with proper answers, the question is, how much should you improve? I think it's a case of playing with the density of mesh point, modifying the mesh, and then observing whether it makes a difference to your simulation or not. So as I was saying before, you can use more accurate elements by going, for example, from linear to quadratic element, as I mentioned before. This is going to improve the accuracy, not always, depends on the problem, but it will also increase the computational efforts that need to be used for the simulation. So most of the time, it's sufficient to start with linear elements, and then afterwards you can try and improve with quadratic if you want. So now that's all I want to say about the finite element method. As you've seen, it's quite a complicated mathematical tool, but the solvers that are available are very, very powerful, and you can use them without deep knowledge of the finite element method. So I'm now going to move to COMSOL multiphysics to show you how we can implement these models. COMSOL multiphysics started as, historically, as I understand, it was the finite element solver part of MATLAB. So it was one of the library of solvers that were based on finite element, but they were developed for MATLAB. The group who was developing this started a separate company. I think it was called FemLab or something like this historically, and then the name changed and it became COMSOL multiphysics. But generally, COMSOL multiphysics is a finite element solver for all sorts of physical engineering and electronics and chemical problems, fluid dynamics, etc. So it's a general package, and it's called multiphysics because it allows you to simulate coupled problems. So in electrochemistry, what can we couple? Well, we can have fluid flow as well as electrochemical response. We can have temperature variations in the material. We can have electrical response of the material. And so each of these physics has its own set of partial differential equations to simulate the response of the system. So COMSOL allows you to combine these different problems and to solve them together. So it consists, so just an example, imagine you pass a current through a conductor. This is going to create Joule effect, so the temperature will rise, and it could be that the material properties are going to change with the temperature. If we had an electrical a chemical reaction, and the temperature rises, then you know that the rate constant would rise according to Arrhenius law. And so you would have a coupling between the chemistry and the passage of the current in the materials around. Another typical problem would be the swelling of a polymer, where you pass some ions, and this leads to solvent ingress, and then your polymer changes shape. A very common problem in electrochemistry is the electrodeposition, where as a function of time, the shape of the electrode changes, like I was talking about edge effects before. Another would be if you have corrosion. You start from a flat surface, and then you create pits wherever the material is corroded. So you have a problem there in that the domain is changing shape with time. COMSOL multiphysics allows you to compute situations where the domain changes as a function of time during the course of the reaction. So you can couple the electrochemistry on the one hand with the change in shape of the domain, etc. So I will only show you one example, which is coupling flow and electrochemistry. But you can see from the COMSOL multiphysics web pages very, very different examples. So COMSOL multiphysics is essentially one made finite element solver and then modules, and you have to buy them separately, and the modules are associated to different kind of problems. So if you go to their web pages, you can have a look at that. I'm not going to go through everything, but for example, here you would have a electromagnetics module, mechanics module, an acoustic fluid flow and heat transfer. And then there's a module here called chemical engineering, where you find most of the modules or submodules which are relevant to electrochemistry. So battery design, fuel cell electrolyzers, electrodeposition, corrosion, electrochemistry. And within that one, you would have electroanalytical chemistry for, say, voltammetry, impedance, etc. Another one that I've highlighted, and it's part of the package, is a material library. So what they have done is they have included a lot of properties of solids and liquids and electrolytes, which you can use as inputs into your system. So I don't know, for example, the variation of conductivity with temperature, or solubility of a gas with temperature, for example. You will find a huge amount of material properties embedded in the software. So I won't go through the whole detail here. I'll leave you to have a look at their web pages. What I've done now is to pick some of the features of the electrochemistry module, just to illustrate the depth to which they go to simulate some really, really complicated problems. So this one I've highlighted is it's the sort of correction that you need to do when you are simulating conduction through complex materials, porous materials, for example. So they have embedded in their module, the electrochemistry module, ways of simulating transport through porous materials. Another one that I've picked here, this is if you want to simulate electrochemical impedance spectroscopy, they allow you to, they have already planned that you want to look at the response in terms of Nyquist plots or Bode diagrams. So they have really thought a lot. Another one, for example, yesterday we were looking at electron transfer kinetics. You see here, you can implement the kinetics at the electrode surface using Butler-Volmer equations, for example. So I'm moving quickly on this because it's, clicked the wrong one. It's available on their web pages. This is just an overview. Again, I'm not going to go through everything. I've just highlighted, but this one is for battery and fuel cell. This is now in the new version of Console. It's now divided in two modules, battery design module and fuel cell and electrolyzer module. Before it used to be one module, but as the software evolves, they are creating more and more applications, and they have now subdivided it in two modules. And I just highlight one just to show you how far they're going. Porosity variation due to dissolution of electrode material during operation by including porosity as a model variable coupled to the charge transfer reaction. So this is a case where you can see that the porosity is changing as a function of time, and therefore as a function of the electron transfer or the electrochemical process. So you have a situation where the structure of the material is evolving with time, and they allow you, they've already programmed the module to simulate this kind of really high level complexity, really. For batteries, they include the involvement of thermal management, thermal runaway, short circuits, aging. So they have already built these kinds of problems that people are desperately trying to simulate nowadays. And you will see a lot of applications of COMSOL multiphysics in batteries and battery research. And they cover a huge range. You will see that there are examples from COMSOL multiphysics themselves, from the company, but there are also examples that are available where people have been simulating batteries and degradation of batteries, etc. So now what I want to do is to show you how we use it. So I'm now going back to the simulation of the microdisc electrode, and I want to show you how we put together the simulation. So when you build your model in COMSOL, you are essentially building a long list, which is there on the right. And this long list starts with parameters. So I will show you how we put together the parameters. Basically, these are the input parameters. And then you've got components, geometry, physics, meshing, study, and then the results. So in the components, in the parameters, well, this is clear. It's just the concentration, the size of the domain, etc. Components, you have all sorts of things. I will show you some more details in a second, but that's where you would define separate variables which are interesting. For example, here I've defined an integration operator. I will show you why. Essentially, I need to calculate the integral of the current density over the radius of the disk. So I've defined an integration operator. I don't want to simulate the domain to infinity, so I've used here from the library of boundaries, I've used what is known as an infinite element domain, which is a way of simulating an infinite boundary at a finite distance. This is where I will define the geometry. We'll see that in a second. This section is where we set up the physics. So this physics is called electroanalysis, because I want to do a voltammogram on a microdisc. And so I've the particular type of partial differential equation defined here. You see, these are my boundaries: axial symmetry, no flux, initial value, that's the initial condition, etc., etc. This section is where we will define the mesh. And then we move on to the solver. So this is what they call study and infinite element domain. Yeah, I will show you that in a minute. I've got examples of an example of that. And then this result section is where we basically extract the information that has been simulated and then plot it, create tables. We can even create reports, etc., etc. So I'm now going to look at all of these, well, not all of these, but most of these in more detail to illustrate how that is implemented. So we start with the parameters, and the straight away you realize that COMSOL multiphysics expects everything in real world quantities. It is possible to do the simulations in dimensionless quantities, but as a basic user, you'll end up doing your simulations in real world quantities. And so when you enter your quantities, so the name is here, so for example, RE is the radius of the electrode, you enter the value and there's a unit. You see the bracket there? stands for micrometer. The concentration is entered as millimole per liter. The potential applied is entered in volts. The diffusion coefficient is entered in meters square per second, but you could enter it in centimeters square per second if you wanted. This is the reaction rate on the electrode surface. So this is the standard rate constant for electron transfer, etc., etc. So automatically COMSOL recalculates the values, and then you can type on the right in this column some information that gives you that explains this quantity. So that's where you enter your parameters right at the top. That's fairly straightforward. Now you come to where you actually define the model. Because it's a simulation of a microdisk, I have selected to use axisymmetric an axisymmetric system, and this is this little symbol here. So when I created the simulation initially, I asked COMSOL multiphysics to work with axisymmetry. So automatically the solver knows that I'm going to be simulating one plane, and not the full 3D geometry. And it knows that is the blue region there, which we're going to simulate. On the definitions, I've defined one variable. So it's here. If you right click on this, you can open the table and then you define your quantity. This is the electrode current. And because I want to integrate the current density over the radius, I've created an integral operator, which is this line here, integral operator. So you click on that, you open up, and then you define your integral. And the important thing here is to tick the bottom where it says compute integral in revolved geometry. And this is where you tell COMSOL multiphysics that you want to calculate the current density with a 2 pi RDR in your integral. There are things that I never use. For example, the boundary system, I never changed that. Elan ITOT is Elan stands for electroanalysis. This is COMSOL's name for that particular physics. ITOT is the total current. It's a variable which is not, so COMSOL multiphysics creates a lot of variables. You can look at all of them, and it's the total current, which is the flux at the current density at that particular spot. It's total because that current density could come from different contributions. The names change depending on the modules that you use and depending on the physics that you use as well. Infinite element domain, I will show you that in a second when we look at the domain. But this is to apply the bulk condition at some finite distance instead of having to go to infinity. So this is the next item in the component after the definitions. We look at geometry. So you create your geometry in many ways. You can import a file from a CAD software, for example, or you can create the geometry yourself within COMSOL multiphysics. They allow you to do all sorts of things. So here we see that the domain consists of this quarter of a circle and then this region here, and it's created by, and the other thing is this point here, which corresponds to the edge of the microdisk. So this is going to be the microdisk, this is going to be the glass, this is going to be the solution, and this is going to be the symmetry axis. So circle 1 defines this domain. Circle 2 will define this domain, and point 1 will define this point. So if I've just opened circle 2 to show you, you can type in here the quantities, and you can decide how to construct the geometries. It's fairly self-explanatory. You define the radius, you define the angle. It's only a quarter of a circle, so you just rotate over 90 degrees. You define the center of the circle, etc. When you finish, you form the union of all your domains, and that creates the overall simulation domain. Now for the physics. So we want to simulate a cyclic voltammogram. So the physics here is called electroanalysis, and that refers to the word elan that I was mentioning before. Within the physics, we've got different bits of information that we need to fill in. So I've just opened up the diffusion bit, and the first thing you need to do is tell the system where that applies. So I've selected 2 regions, the inner region and the outer region, which are numbered 1 and 2 there. And in that, I tell the system that I want to simply have a diffusion. So that sets the partial differential equation for diffusion in axisymmetric coordinates. And I type in the value of the diffusion coefficients for species 1 and for species 2. You see, automatically, COMSOL Multiphysics has created names for the species. You can change those names. If I had 3 species, I would tell the system to give me 3 species, and it would solve for 3 partial differential equations. Now, this electroanalysis thing is one physics that's available from a library of problems. If I wanted to do electrodeposition or fuel cell, there would be a different physics that you would use there. Initial condition is obviously where you set the initial concentration. So you first tell where this applies. So again, my 2 regions here, and then you go in and you input the concentrations that you want for the relevant species. Notice that COMSOL Multiphysics is already checking that what you are entering has the right unit. So if you enter a variable here, which is not defined as a concentration, it will flag it and it will tell you there's a problem. So in that respect, working with real world units in COMSOL Multiphysics is very powerful, because it checks for the self-consistency of all the information that you supply to the system. Now, in these 4 diagrams, I illustrate how to implement the boundary conditions. So on the actual symmetry, I enter the condition that applies to this region. See, when I click on that, it knows, by virtue of the fact that it's an axisymmetric domain, it knows it's this boundary. And in fact, I don't need to do anything, because COMSOL Multiphysics knows by the way it's being created, it knows that on this boundary there will be no flux across the wall there. On this one here, it's a no flux boundary, because this is the piece of glass around the microelectrode, and this is where there is no reactivity, so no consumption, no production of species. So I will define this as a no flux boundary. Again, I just need to select no flux boundary. Automatically, COMSOL Multiphysics knows what condition to apply at that point. This one is a concentration condition, and I select this boundary, which is the far field boundary, and I tell COMSOL Multiphysics that on this far field boundary, I want to impose the bulk concentration. And this is simply, you would just enter the value of the concentration, and it will impose it in this boundary. And then there is the the boundary that corresponds to the microdisc electrode. So this is called electrode surface, and then you can see there is a subset here. So I need to show you how we deal with that. But the other thing I want to show you is that this internal boundary is simply, as you will see when we look at meshes, it's simply a boundary which defines two different meshes, but it's not a boundary where I need to impose a particular condition either of flux or concentration. It's purely because I want to define two different families of mesh within these regions. So if I click on the electrode surface, of course, I need to identify the correct boundary. So I need to select it. And then I need to say what's happening on the electrode surface. So on the electrode surface, I'm going to impose the potential because it's a voltammogram. So I want to sweep the potential. And you can impose this versus the reference electrode. So COMSOL multiphysics allows you to select different reference electrodes. It allows you to even select how the reference electrode potential depends on temperature. So there's a lot that goes in there. And you can impose that with respect to an electrical reference potential. Now, if I click on the sub-element, which is called the electrode reaction, you can see there is a lot more information that goes in. And here, you need to define the stoichiometry of your reaction. So you need to enter the number of electrons involved, the stoichiometry for the reactant and the product back here. And then if you click and open up this window, you will see, for example, model input. No, phi ref equals 0 doesn't mean it's SHE. This is just, that would be defined elsewhere. Phi ref equals 0 would be the electrical reference potential, for example, with respect to the vacuum or something like that. Because in COMSOL multiphysics, you can also input, because you can couple the electrochemistry with the material properties. You could have the electrical potential in the metal with respect to ground, and then you could have the electrochemical potential with respect to a reference electrode. So there are many ways of controlling potentials in COMSOL multiphysics. You see when you click on what is the equilibrium potential, you can define your equilibrium potential. You can even define how it changes with temperature. You can even define the reference temperature, and they even show you how this is going to be varied according to temperature if the temperature were to change during your simulation. If I click on electrode kinetics, you see this this bit here where you can choose different expressions to control the kinetics. So here I chose the Butler-Volmer expression, and this is essentially what you saw yesterday when I was simulating the role of electron transfer kinetics on the shape of the voltammogram. So you've got your standard rate constant for electron transfer. It already knows that it should be in meter per second or centimeter per second. And here you don't need to enter a number. You can just enter the variable, which was defined earlier in the table of parameters. And then you've got your transfer coefficient. So you can see that COMSOL multiphysics is already prepared to deal with electrochemical problems. This is why you pay extra for the electrochemical module, because what they have done is they have already selected a lot of the inputs to be designed for the type of problems that we encounter in electrochemistry. But more than that, when we talk about solvers, you will see that they have already selected solvers which are appropriate for the electrochemical problem. So that is very helpful. Now I come to the mesh, and this is where I talk about the different regions. The mesh is defined in this component here, and there are different parts to it, and I will open up more information as I click on these things. So here we have three regions, essentially. We have a region here, which is a lot of solution there. Then we have an outer region, and you can see the shape of the mesh is very different. In the inner region, they are triangles of different size and shape, whereas on the outer region is a mapped mesh, which is a kind of rectangular distribution. And then we have a third region, which is what is happening very, very close to the edge of the microdisc electrode. So this is where you need to have a little bit of practice and essentially observe by what others have done and get a feel for how the mesh works. But the reason for defining these three regions is A, you want to have this far field boundary. Instead of saying simulation all the way to infinity in terms of R and Z, you don't want to do that. You define a region which is known as an infinite element. So there was a question earlier about the meaning of the infinite element. This is it here. The infinite element defines this region, and it's an element that was introduced in quantum multiphysics a few years ago, which basically is a mathematical adjustment of the far field, the infinite boundary, right close to something which is realistic, but it has mathematically the same effect as putting the far field boundary at infinity. Now, for most of our electrochemical simulations, this is not necessary because always our domain is finite. I mean, if you put your electrodes in a cell, the walls of your cell are a few centimeters away, so you don't need to simulate to infinity. So you can approximate to the actual cell dimensions. So there's a particular mesh here because of this region. The triangular mesh is very, very common in quantum multiphysics. This is probably the mesh that free triangular, the mesh that you would use most of the time. But if you look at, for example, in engineering and so on, they would use different kinds of mesh. And then I need to move on and show you how we construct these meshes. So if I click on size here, I can set, I can use a predefined mesh. So quantum multiphysics as a whole, something like 9 different levels of mesh, or I can set it myself. And I can set it myself by defining the maximum element size. So this would be the length of the maximum length of one of the sides of the triangles, or the smallest length of triangle side, or I could choose the growth rate, so how the triangles are getting bigger, etc., etc. So there's a lot of control that you have. This is where you have to do some trial and error, because I personally don't know how to. I will show you some examples, but generally I don't know how to optimize the mesh. I know to some extent, but not everywhere. I know that for this particular region, which is the edge of the microelectrode, where you have a discontinuity in the boundary condition between imposing the concentration on the microelectrode and imposing the flux on the insulator, I know that this region is critical. This is where, you know, even before we were doing simulations, we knew that electrode deposition was much, much, much stronger in this region because of the edge effect. So here, I know how to constrain the mesh. I choose a custom mesh size, and I make the maximum element size to be a fraction of the radius of the electrode. So here I just say, make the mesh here no bigger than 1/100th of the radius of the microelectrode. So imagine if this is 1 micrometer, that means that the mesh will not be bigger than 10 nanometers. Okay, which means the smallest mesh next to that boundary will be no bigger than 10 nanometers. Further away, it will expand, but I've imposed a mesh constraint at that particular point. Is it sufficient? That's where you need to do trial and errors, because I can't tell. I observe, I look at the current, and if it's sufficient, I accept it. I might try to use a coarser mesh and optimize the mesh by trial and error. But at least for that region, I know roughly what to do. Far away in the solution, I just let COMSOL assign the mesh as it wants. Now, I move to the almost the last step is the study. In the study, we have to define the solver, and this is where you could pick all sorts of solvers. So this one is a stationary simulation because we want to simulate the steady state to the microelectrode, and so you choose a steady state solver. But if you wanted to do a transient simulation or an AC impedance simulation, that you would choose different solvers, and they are available from a library of solvers. And these have been pre-selected or pre-tuned for the electrochemical problem of interest. Here there is what we call the parametric sweep. And the parametric sweep is where you tell the system to repeat the simulation over and over again, this time for different input potentials. And that will set the potential applied to the electrode, and it will generate the voltammogram by repeating the simulation over and over again. All these parameters were entered in the list of parameters right at the start. You can tweak the solver parameters here, but I generally don't play with that very much. Again, you need a fair amount of mathematical knowledge and how each solver behaves. COMSOL multiphysics provides a lot of information, but it takes time to really tweak these things. So the last section is the results. This is towards the bottom of the tree. So we're now looking at how to exploit the results of the simulation. So you can produce maps. So this is a 2D map of the concentration profile. So this is along R and this is along Z. And there's a color code which corresponds to here red for high concentrations and blue for low concentrations. And this is basically showing you the concentration, the diffusion layer thickness, essentially. And this is the region where diffusion has created the local gradient. You can also plot it in 3D if you want, because you have a symmetry of revolution. And then you can create 1D plots. And in this case, the one I've selected is simply the current against the applied potential. So the potential was varied. For each potential, there was a different simulation, and put together, you can create that current. So what is the meaning of a mesh at a point? You are imposing at a particular point, you are imposing the constraint on the mesh, which is adjacent to the point. So there will be one node probably on that point, but around the point of interest in the solution, there is a mesh, and the mesh propagates from there. And so if you impose a constraint at a particular location, I could impose a constraint on a point, on a line, on a surface. There are many ways of constraining the mesh. I could have imposed the constraint on the electrode radius and have a particular distribution of mesh along that radius. That's another way of doing it. But here, the simplest way is just to say that all the mesh elements adjacent to that point cannot be bigger than a hundredth of the radius of the microelectrode. So now what I want to show you is, with the last example, is how we can embed in the simulation some more complex transport equations. So and I want to show you that because the finite element method is pretty good at doing that. So you've seen when we were doing the finite difference experiment yesterday that we have a term which is for transport, and then if we have coupled chemical reactions, we can have some kinetic terms. Okay, so in COMSOL multiphysics, you could include some couple chemical reactions, and it would automatically increase the complexity of the partial differential equation. I just want to focus on the mass transport terms. So I've now subdivided them according to 3 contributions. One is change of concentration due to a diffusion flux, or to a migration flux, or to a convection flux. And if we have kinetic terms, then of course they would come as additional terms to that. So what I will do now is look at that in more detail to move towards the simulation of the channel flow cell. So whenever you have different forms of mass transport, you are essentially using the Nernst-Planck equation. So I've just written it here in terms of 1D, but of course, when we do this of X, Y, Z, or R and Z. So we've got a diffusion term, we've got a migration term. As soon as you involve migration, you see there is a new variable. It's the potential. So you need now to include boundary conditions for your potential. It's not just boundary conditions for the concentrations. You now have to include boundary conditions for the distribution of potentials within the domain. So the complexity goes up. And then for convection, you now need to account for the velocity of the solution as a function of space and time. So I'm going to ignore migration and just focus on diffusion and convection. So this is the flux. And I wrote it here in 1D, but for 2D, you would have X, Y. And the flux will be defined according to a diffusion term and then a convection term. So we'll see how we can implement that. Oops. So this is the last example I want to cover in this lecture. And it's a channel flow cell. So we've got a channel in blue. The solution comes from the left, and it comes out of the channel on the right. At the bottom of the channel, I have a microband. So you imagine the microband is going into or out of your screen. It's a 2D problem because I don't need to simulate every cross-section, just one cross-section is sufficient. And so I just need to simulate the concentration distribution within this blue region. Now, because we have a flow in a pipe, we have several options. So the simplest option is to start with a velocity distribution based on a parabolic flow profile, which is what you would have for laminar flow, which is the simplest flow you can think of, okay? And for that, you will see it's good because we have an analytical solution which tells us exactly the velocity as a function of distance away from the walls. So I will use this to define the velocity of my solution. Now I'm going to move around the boundaries and impose the boundary conditions. At the beginning, I imposed fixed concentration because that's upstream, so nothing has happened here. So I know the concentration everywhere. On the upper wall, which is not an electrode, it's inert, I impose dc dy equals 0, no flux perpendicular to the wall. On the outer outlet, I impose no flux in either X or Y. It's purely convection here. There's no diffusion involved. The channel is long enough to make sure there is no diffusion involved in that region. Along the bottom here, I have an inert wall, so dc dy equals 0 again. On the electrode surface, I've imposed 0 surface concentration. And then on the rest of the inert wall here, I've got no flux. So when you look at the transport equation, you've got a diffusion term here, which is in terms of X and Y. And I have a velocity term, which has diffusion downstream and velocity, which depends on Y. So essentially what you see is that the convection is shifting the solution downstream along X, but the velocity is only in terms of Y. So this is analytical expression for the velocity as a function of the distance inside the channel, the distance y. H is the channel height. And this comes from solving the flow profile within the channel. And it's based on laminar flow. If you don't use the analytical equation, you can ask CONSOL Multiphysics to simulate the flow profile, having obviously set up the proper physics for laminar flow. You can do that before you do the electrochemical simulation, or you can do it at the same time as the electrochemical simulation through coupled physics. So these are results of the flow profile. So this is a map of the channel. So upstream is on the left, downstream is on the right. The microelectrode is down in the bottom here. And what we see is a color map of the velocity. When it's blue, it's very, very low value. And when it's red, it's a high value. And laminar flow gives you this low velocity next to the wall, high velocity in the middle, and then go back to low velocity towards the wall here. And it's this parabolic flow profile, which I have got here. So this is going to be used as an input into the electrochemical simulation. But as I said earlier, I could actually solve the two problems at the same time if I wanted to. I've done that, but I don't have time to show you this now. So I'm just showing you the simplest case, which is using the analytical solution at the moment. This is the model setup for this problem. So we've got all this is a big table of parameters, and they go here. This is the physics. So it's still electroanalysis, but now fusion and convection. And now you have more boundaries to define, because you have boundaries in terms of concentration, but also boundaries in terms of fluid flow. So you see there's one here called inflow, and the other one is outflow. So there you say that you have the bulk concentration on the inflow boundary, and then on the outflow boundary you set up your no flux conditions. The mesh, I won't have time to show you the mesh, but it's obviously, I have two edge effects, one edge upstream and one edge downstream, the two edges of the microelectrode. So you would want to define high density of mesh points on both sides. It's a transient simulation here. I want to show you the evolution of the concentration profile, and I will be doing a parametric sweep because I want to vary the solution velocity to show you how the concentration changes for different flow rates into the channel. Okay, so in terms of results, what do I want to see? Well, of course, I want to see the current as a function of time. So I will show you this later on. I want to see the velocity map, just to make sure it's doing the right thing. I want to see the velocity profile at a particular area. I want to compute the electrode potential. So I might want to do a voltammogram there if I change it. And also I want to see concentration maps. So you can see that with CONSOL Multiphysics, we can exploit a lot of information from the simulation. Let me show you this point here. It says cut line 2D. This is a way of extracting additional information by taking cross sections. This is to plot the velocity, and is to create this plot. I just wanted to extract the velocity from the as a plot against the y-axis. This is the y-axis. Okay, but essentially the whole data set is here. This is where you have concentration as a function of x, y, t, and the inlet velocity, because with the parametric sweep, I've created a lot of simulations for different inlet velocities. So let's look at some of these in a little more detail. This is a typical concentration map. And what I've added on it is arrows which simulate, well, which illustrate the velocity in the channel. So the length of the arrows actually represents the change in velocity as a function of where you are in the channel. The color code corresponds to the concentration. So we can see that upstream of the microelectrode, nothing's happening, the concentration is the same. And then when we come close to the microelectrode, we can see that far away, the concentration is not affected. But as we come close to the microelectrode, we see the concentration profile changing, and this is evidence of the consumption of the reactant. This is the concentration of the reactant. Okay, so we see that on the electrode surface, the reactant is consumed. Blue corresponds to 0. But what's interesting is this plume here, and that indicates that the consumption of the reactant is felt downstream, and this is evidence of the combination of convection and diffusion within the channel. So this is at a particular time, or at long time if you want. I want to show you how this evolves with time. So here is not with time, with velocity. Here are channel distribution or concentration distributions within the channel, but simulations performed for different inlet velocities. So this is a very, very low velocity. So essentially the solution is stagnant, and this is a very high velocity. So now we are passing the solution really, really quickly in front of the electrode. So in this region, we've got virtually no convection, and you can see that the shape of the diffusion field here is entirely controlled by diffusion. But if I crank up the velocity by a factor of 10, you can see that the diffusion layer is distorted. If I crank up by another factor of 10, you can see this plume, which is dragging downstream quite a long way. And then if you crank up by another factor of 10, now you can see the boundary layer is very, very thin. Most of the channel is not affected by diffusion, except for a skin of solution right close to the wall here. So without extracting numbers, I can use the map to check qualitatively whether the simulation is working or not. But of course, I can go beyond that, and I can extract some numbers. So I can calculate the current by integrating the current density over the length of the electrode. I can calculate the current, and this is the current plotted as a function of time. So it's a log-log plot, because I've started from very, very short times, 10 nanoseconds, and I've gone up to about 1 second. So you can see that, and I've got a log scale here because I can see that the simulation is struggling at the beginning. You can see there are some issues, and it's a bit like what I showed you with the finite difference. Even finite element requires some time to settle to the right, to converge to the right answer. So I would say that this region is used up for conversions, but it's only, we're not, it's short of a microsecond is here. So I always do my time-dependent simulations that way, so that I can see how long it takes for the solver to converge and then to stabilize. I can see there is something strange in this region, because essentially I would expect the current to be dependent on time according to t to the minus half, because at very, very, very short times, they should be planar diffusion. So I would expect a slope here on the log-log plot to be minus half, which is about right here, but it's not right there. It shouldn't plateau like this. So I think maybe if I redid this simulation, I would need to repeat it for with different time steps, for example. And that's where you need to go into the solver to tweak things. Now I've got 1, 2, 3, 4 simulations here, and they have all been done. They've been done with different flow rates. So at very, very low flow rate, you can see the blue line. The current keeps decaying. at faster flow rate, the green line, the current reaches a plateau. At the red line, higher flow rate, the red line, the plateau corresponds to a higher current and is established much sooner. And then at the extremely high flow rate, you can see that the plateau is current. This is evidence of steady state behavior introduced by the combination of convection and diffusion. And you can see that when I crank up the flow rate, the limiting current is increasing because effectively, when you look at the diffusion layer thickness, it's big when you have low flow rate, and it becomes very, very, very thin when you have very high flow rate. If you have a very, very thin diffusion layer, the gradient, imagine the electrode is like this. If you have a large diffusion layer, the gradient is shallow, that's a low current. If you have a very, very thin diffusion layer, the gradient now becomes very, very steep. That means it's a high current. We have evidence here of this just by looking at the magnitude of the current at long times. So I think this is, I'm at the end. How can you take this further? Well, I've mentioned commercial solvers. So for 2D, I recommend COMSOL multiphysics, but there are other finite element packages around. Certainly, this is the one which has the most, has been developed the most for electrochemical problems. I recommend for 1D problems, 2 commercial solvers, DGSIM and DGELC. They are one-dimensional, they work extremely well. You can even do rotating disk, and you can even do micro disk electrode. DGELC has a finite element solver built in, so you can do 2-dimensional simulations as well in there. And they're really, really geared up for electrochemistry, so they're very good for that. If you are keen on modeling yourself, then you can go into MATLAB, because in MATLAB, you've got a whole library of solvers for ODEs and PDEs, including finite element, because that was where COMSOL multiphysics started. And then if you are interested in open source, there is a finite difference method solver called Soft Potato, which means software potentiostat, from a former student of mine, Oliver Rodriguez. And Oliver is continually improving his simulation. This is it here, if you are interested. And it's essentially designed for electrochemists. So you can design different waveforms. You can include electron transfer kinetics. You can look at current as a function of time, current as a function of potential. You can look at concentrations as a function of distance and time for both the reactant and the product. You have all sorts of parameters. So if you want to play with a simulator, this one is evolving, but at the moment it's already pretty useful if you've never done any simulation and you can't afford to buy one of the commercial ones. Have a look at this one. And I think that is the end. So I've listed some key points here. I don't want to go through that because I've spoken quite a lot already. I see you didn't use the plot output of COMSOL. Yes, I did, because I plotted the concentration maps are 2D plots. The current as a function of time is a 1D plot. Page 44. Which one is that? I don't know. Sorry. 44, 2, 3 back. This one. So on this one, page 40. I
think
no.
It's 44.
Well, 44, there is.
Is this one, Hona?
I don't understand the question. There is no plot here before. I don't know where the question applies. This is a plot straight from console. It's a 1D plot. Okay, so I use it all the time, even to plot the velocity as a function of space within the channel. That was a 1D plot. Oh, I mean, you can use console multiphysics to create all sorts of plots. I don't export to MATLAB. What I do most of the time with console multiphysics is to export a table of numbers, which could be current as a function of time, or current as a function of potential, or concentration profile. I just export that as a table and paste it into Excel or Origin or whatever plotting package you want to use. Console multiphysics has pretty good plotting package, but if you want to do something which is for publication or for a dissertation, then I would recommend using another plotting package. But I mean, for tweaking and running simulations, you can just rely on the plots that I've shown you here, which comes from the console multiphysics software.
Perfect. More questions? No more questions here in the chat. Guy, thank you very much, Guy, to help us with the school, and it's amazing to see now the interfaces, how to put the parameters. It's what is really important to close off these simulations and to understand how to do that. Thank you very much. Say thank you to Oliver to put his effort to develop the soft potato. It's very good one. I try to use in my classes here in Brazil, and say thank you to him. And thank you very much to you to help us with the school again. And thank you very much. There is a lot of participants say thank you to you through in the chat.
Okay.
And with this, I would like to say thank you for everybody here today in the room, in the Zoom room, and on the YouTube. And probably, if it's possible, come here tomorrow to take a picture in the end, if it's possible.
At the very end. So
yeah, close to the end. It's like for the midday here in Brazil. It's like it's okay. For you. It's 3 p.m. probably.
Okay.
Yeah. Thank you again. Yeah. Good night.
Thank you, everyone.
See you. Bye bye.
Thank you, Thiago. Cheers. Bye.
Cheers.
Bye.
Thank you again. See you tomorrow.